side the last time, so I will correct it. I will use that opportunity to correct it. In fact, you did kind of you did correct me. And the oversight was that you actually straddle the physics and the chemistry community with equal ease. And actually, I mean, yeah, you publish more in physics journals, I suppose, than in chemistry. So, and my point in the previous introduction was that you actually have traveled much further than most people who came into doing ion trapping and so on and so forth. And that was essentially the point I was trying to make. So,
okay. Yeah, thanks, Arik. That's very kind of you. Yeah, I mean, if you want to put it that way, I've always been a bit schizophrenic, right? I have always been both a chemist and a physicist. And as a matter of fact, this is also what I've been enjoying a lot about this, right? I mean, having a foot in both of these worlds, right? And trying to bring them together. And yeah, I think.
Sorry, please carry on.
Yeah, no, it's fine. It's good.
Yeah, so should I start, Sourav?
Yeah, we can start. I mean, it's okay, I think.
Okay, so it gives me great pleasure to re-welcome Professor Stefan Willitsch from the University of Basel to give his second talk on cold molecular ions and traps, methods and applications. Over to you, Stefan.
Thank you very much, Sadiq. It's a great pleasure to be with you again, and I thank you all for joining me for this second lecture. I have sent the organizers an updated version of my slides here because I've added a few more things, and I hope they will upload them to the website soon, so so that you can also upload your notes if you like to. Okay, so my second lecture will deal with cold ion neutral interactions. So during my first lecture, we have been talking about cold molecular ions, the basic techniques behind them, and mostly applications in spectroscopy and in quantum technology. And during my second lecture, we will talk about cold ion neutral interaction with particular emphasis on ion-atom hybrid systems, as the organizers have asked me to specifically talk about that. So that will be the focus of the talk. And I will start with a short introduction to the theory of ion neutral interactions, insofar as we will need it to understand the various experiments that I will be talking in the second half of my talk. Okay, so let's talk about ion neutral interactions a bit. And I'd like to start with recapitulating some elements from classical collision theory, just to introduce the salient concepts and also quantities that we will need later on. So just to start this, let me remind you that there are three types of collision events that are important, right? So when I talk about interactions here, what we mean with interactions is in the end, well, this always boils down to collisions, right? So we'll be talking about collisions. And there are three classes of collisions that are relevant for our topic here. The first one is elastic collisions, right? And this is collisions where the total kinetic energy and therefore also the internal state of the collision partners are observed, right? So like in a classical billiard game, if you like. Then we have inelastic collisions. And this is the case when the total kinetic energy and the internal state of the collision partners can change during the collision and the interaction, but their chemical structure is still conserved. And then in the end, we have reactive collisions, and that is the most complicated of all of them. And this is where all of this changes, right? Kinetic energy changes, internal state changes, and also the chemical structure can change. And we will encounter all three types of these processes over the course of this lecture. So let me focus to begin with on elastic collisions, because that's the simplest case we can have. And I will use this example to introduce some of the salient concepts. Let's, for the sake of the argument, first consider just the collision of two structureless particles, right? You can think of this as a classical billiard game, or if you will, two atoms, structureless atoms that collide with one another. And we are always dealing with these problems within the center of mass frame. Yeah? So we are not in the laboratory frame, but we transform the whole problem in the center of mass frame, where we separate the collision problem into a motion of the center of mass of the two collision partners and their relative motion. And for the collision dynamics, what is always important is just the relative motion of the two particles. Okay, so what you see here is a cartoon of a classical collision trajectory in the center of mass frame. So what we have here is, we have essentially two coordinates that suffice to describe this problem, because essentially it has cylindrical symmetry. So that is the distance or the relative position vector between our two particles, right? And for the sake of these cartoons, you can picture it as, you know, you have one collision partner here in the center and the other one approaches on this trajectory, right? Just for the sake of visualizing it. But remember, again, this is in the center of mass frame. And then we have an initial velocity vector that describes the approach of those two. So we then have an orientation angle, yeah, which is the angle between the relative position vector and the initial velocity vector. And you see here the collision trajectory, right? And during such an elastic collision, what typically happens is, I mean, the velocity vector gets deflected by a certain deflection angle. What is also an important quantity is this impact parameter here. And the impact parameter you can understand is if you draw a parallel line between the initial velocity vector, right, and the line that goes through the center of the of this coordinate system, then you have here the asymptotic perpendicular distance between these two lines is what is called the impact parameter. And this impact parameter will play an important role later on. Okay, now let's have a look at some salient physical quantities. One of them is, as usual, the angular momentum. And in classical mechanics, the angular momentum L, the vector, is defined as mu times v vector product with r. Mu is the reduced mass of the collision, v is the relative velocity vector, and r is the relative position vector. Now, if we want to calculate the magnitude of this angular momentum, then we have to calculate the magnitude of this vector product. And we can express this by this identity. So the magnitude of this vector product can be cast into this scalar product here. We have mu times v scalar product with r sine of psi. Now, if you look at this expression here, r times sine of psi, then you realize that this is nothing else than this impact parameter, right? So we can express the magnitude of this angular momentum as mu times v times the impact parameter b. Okay, so this means that L is proportional to b. The magnitude of this, the angular momentum of this collision is proportional to b. Yeah. So, and since angular momentum is conserved here, so L before the collision is the same as L after the collision, this means that we can calculate the angular momentum for this entire process with this simple relationship. Okay, so this is an important result. So the other salient quantity is, of course, the total energy in this whole problem. And of course, we have kinetic energy. Then we have potential energy. This is the energy that comes from the interaction between the two particles, the interaction potential. So that is nothing surprising. What may be not so obvious in the first place is that we also have a third component, and that is the centrifugal energy. And the centrifugal energy, well, this is the energy that is associated with a rotational motion. And what is the rotational motion here? Well, the rotational motion is essentially, this is the rotation of this relative position vector about this orientation angle psi over the course of the collision. Okay, so in general, with collisional process, there's also this rotational component involved, and that is what gives rise to a centrifugal energy, right? In classical mechanics, the centrifugal energy can be expressed by this term here. So it's 1/2 mu times r squared times psi dot squared. And psi dot is the time derivative of this orientation angle. So it's the angular velocity by which this orientation vector, the relative position vector, is termed during the collision. So we can now use this result, namely that the angular momentum can be expressed as mu r squared times omega. And so we can insert this into the centrifugal energy and derive at the result that the centrifugal energy can be cast into 1/2 L squared over mu r squared. So in other words, the centrifugal energy is not surprisingly a function of the collisional angular momentum. So for the total energy, we arrive at this result then. We have the kinetic energy, we have the potential energy, we have the centrifugal energy. And those two last terms, they're usually lumped together to a new effective potential, a centrifugally corrected potential, right? Because the centrifugal energy disappears essentially as a contribution to the potential part of the problem. Okay, so what one is also interested in is, of course, cross sections, right? And in a simple hard sphere approximation, so the billiard ball game, if you like, one can express the cross section simply as pi times b squared max. And this b squared max is the maximum impact parameter at which a collision still happens. And what one often measures in an experiment is actually a rate constant, yeah, how fast the process happens, at which rate the process happens. So the constant associated with this quantity, and this rate constant can be expressed as sigma, the cross section, times the relative velocity. Okay, so these are important quantities that become relevant in experiments. So let me say a few more words about this centrifugally corrected potential, because this will play an important role in what comes later on. So I've already said that the centrifugal energy, that's the energy that's taken up in the rotation of the position vector. And the collisional angular momentum, well, this is the associated angular momentum with that rotational motion. So it's the angular momentum that is that goes along with the rotation of r about psi. And if you now look at the form of this effective centrifugally corrected potential, then you see it has these two components as discussed. If you look at typical interaction potentials between atoms, but also between molecules, then they typically have qualitatively this sort of shape, yeah, as a function of the distance between the two particles r. They have an attractive part, which is usually long range. And if the particles come too close together, then there is a repulsive part, which essentially stems from qualitatively from the repulsion of the electron clouds around the particles when they come too close together. So we have attractive and repulsive parts in the interaction potential. However, if you look at the centrifugal part of the potential, then this is always positive, meaning repulsive, right? Because all these quantities are always larger than zero. So this means that whenever we have centrifugal energy, it adds a repulsive component to the whole problem. And this can be seen here. So here, this curve is just the interaction potential without any centrifugal part. And if L, the angular momentum of the collision, becomes non-zero, then we see that the barrier builds up here. And that is the infamous centrifugal barrier that arises because of the angular momentum in the collision. And the larger L, right, the larger this barrier becomes. And in an extreme case, yeah, the effective potential becomes totally repulsive of the collision. So that means is that this centrifugal energy plays an eminent role, yeah, in collisional processes. And we will see more details over the course of this lecture. Okay, so let's talk a bit more about interactions between ions and neutral. In other words, let's talk a bit more about this interaction potential V of R. And our topic is ion-neutral interactions. And thankfully, one has to say, it turns out that ion-neutral interactions are very often governed just by the long-range part of the interaction potential, meaning the attractive long-range part that I have been referring to. And this long-range part can usually be expressed as a power series in the internuclear distance. Yeah? This is a multipole expansion of all these long-range interactions that one does here as a function of the internuclear distance. And one can see that, yeah, we have terms in R squared, R cubed, R power 4, this should be a superscript here, and so forth. And the task is now to just figure out what these different coefficients are for different scenarios of collisions that one has. So the first term here, sort of, there would also be a C1 term, right? But the C1 term would just be a Coulomb interaction. And since we are dealing with ion neutral interactions, this term is not relevant. So the leading term is then, under certain cases, the C2 term in this series expansion. And this term corresponds to a charge dipole interaction. As to the interaction between the charge of one of the collision partners and the permanent dipole moment in the other collision partner. But for this to be non-zero, the other collision partners needs to have a permanent dipole moment. Yeah. So, and in other words, this is usually a case when we have molecules. Yeah, because atoms don't have permanent dipole moments. So, and then in this case, the C2 coefficient can assumes this form. So we have the dipole moment of the neutral molecule, and then there is, of course, an orientation dependence. Yeah, if that is the charge, if that is the dipole moment, then of course it depends on how the dipole moment is oriented with respect to the charge. Yeah, so this is the leading term if we have an interaction between an ion and the polar molecule. If the molecule is not polar, or if it is an atom in certain states, then we do not have this term, and the leading term is then this C3 term. And the C3 term corresponds to an ion quadrupole interaction. Yeah, so this is where the charge of the ion interacts with a quadrupole moment in its counterpart. And this is the case when the interaction partner is an atom in a non-spherical symmetric state, meaning a PD or an F angular momentum state, or if it is also an apolar molecule, right, which doesn't have a dipolar moment, but then it usually has a quadrupole moment. And if it's a molecule, then the C3 term, this is usually expressed in this form here. So Q is the quadrupole moment of the neutral molecule, right? So if we stick to a linear molecule, then this is usually taken as the largest entry in the quadrupole tensor. And then again, we have an orientation dependence here expressed with this cosine squared of theta term. If the counterpart is an atom in a PEDF or higher angular momentum state, then one can calculate the C3 term from spherical tensor algebra and derives at an expression like this. And one sees here that one has a Wigner-free J symbol in this expression and the reduced matrix element of the quadrupole moment tensor. Okay, so with this you can calculate this multiple coefficient C2 and C3. If neither of these terms applies, then the next leading term is the C4 term. And this arises because of an ion-induced dipole interaction. Yeah, and this is the leading term if the neutral counterpart is a structureless polarizable particle, yeah, say an atom in an S state. Yeah. Or it could also be an apolar molecule with a very small quadrupole moment, which can be neglected for practical purposes. And this C4 term is then given as 1/2 times alpha, and alpha is the scalar polarizability of the neutral. This is also often called the Langevin interaction, and this will play again also an important role later on. I should also add that usually the C4 term also contains an anisotropic component, right? Because nothing really is really perfectly structured. Okay, but this is certainly the leading term, and this is the one that we will be considering henceforth. Okay, so I said ion neutral interactions can very often just be understood in terms of this long range interaction. And if that is the case, right, then collisions between ions and neutral often follow what is called capture dynamics. Yeah, and that is exactly what this refers to, namely that the collision is completely governed by the long range interactions, and short range interactions between the particles then do not play a role. And one of the most important cases of such a capture, processes between ions and neutrals is so-called Langevin capture. And that is the case when the long-range interaction is dominated by this Langevin interaction, so the ion-induced dipole interaction, the C4 term. Okay, so how can one understand these capture processes? And this Langevin capture is usually treated within the framework of classical collision and capture theory. And this can be understood rather simply, actually. So what I've plotted here is again the effective interaction potential that we have discussed. So the interaction potential plus the centrifugal potential as a function of the internuclear distance. And they only focus on the long range part, right, where we also see the centrifugal barrier. So for a successful collision to happen, the two collision partners essentially then have to overcome the centrifugal barrier. Okay, so remember, that is the form of this effective potential. We have the centrifugal part, we have the interaction part. This one is usually attractive, as we have seen. And this one is always repulsive and leads to the centrifugal barrier. And what is now important to remember is the expression for the classical angular momentum, right? This is given by mu times v times b, and b is again the impact parameter. So for a collision to be successful, meaning that the two particles can come close to another, right? They have to surmount the centrifugal barrier, right? So this means that the collision energy with which the two particles come in needs to be high enough so that they can surmount the centrifugal barrier and come to close interparticle distances, right? Where then the collision really happens. So for this to happen, right, so we have this condition, right? So this means that the collision energy, right, must be at least equal to the maximum of the effective potential, right? And since the effective potential is linked to the angular momentum of the collision, and the angular momentum is linked to the impact parameter, there is a maximum angular momentum and therefore a maximum impact parameter at a certain collision energy which fulfills this condition. Okay? So, and then from this condition, one can work out what this maximum impact parameter needs to be so that the height of the centrifugal barrier is just equal to the collision energy. From that, one can work out the maximum impact parameter, and then from the maximum impact parameter, one can work out the collision cross-section. And from the collision cross-section, one can then work out the rate constant for the collision. And with that, one has everything that one needs already. Okay? So the picture that we have here is that in this classical capture theory, the collision energy needs to be high enough in order to surmount the centrifugal barrier in the effective potential. This gives me a condition for the maximum impact parameter that the collision can have. And the maximum impact parameter is then linked to the cross-section and the cross-section to the rate constant. So that is the rationale. So if now this long-range interaction potential is dominated by the Langevin interaction, meaning the ion-induced dipole interaction, and I give it again here, this time in SI units, then one can work out from this collision the cross-section and the rate constant for this specific potential. And one finds that the cross-section has this form and the rate constant has this particular form. And now let's just focus on the rate constant for a moment. We see that it is actually quite simple, right? It's the square root of pi times alpha prime. Alpha prime is the polarizability volume of the neutral. Yeah, so it's the polarizability divided by 4 pi epsilon naught. E squared, this is the elementary charge squared. Epsilon naught is the electric field constant, and mu is the reduced mass of the collision, right? So we only have two parameters, two system-specific parameters that play a role here: the reduced mass, right, and the polarizability of the neutral. So it's a very simple expression for the rate constant that one gets here. And the important thing to note here is also that it is independent of the collision energy, and therefore also independent of the temperature, the collision temperature, right? So we have, meaning if we have Langevin capture dynamics in an ion neutral collision, then the rate constant is constant with temperature and therefore also with collision energy. So that is an important result here. Okay, so that was classical collision theory and applied to classical capture theory. Let me just say a few words about the quantum treatment of these processes. I mean, this is a topic about which I could lecture an entire term. Let me just recapitulate a few important points here. So if we cast the same problem, right, elastic scattering of two structural particles into a quantum mechanical framework, then, okay, we have to set up the Schrödinger equation for this problem. And the Schrödinger equation in spherical coordinates is given here, right? So it's again the Schrödinger equation in terms of R, and there is also the orientation angle theta, psi as we have called it before, involved. And this is ingrained here in the angular momentum operator. So we have here, again, the kinetic energy operator. We again have a term that corresponds to the centrifugal energy of the problem. And again, we have the potential energy. And as a matter of fact, this Schrödinger equation that you get here, that you have here, right, is the same Schrödinger equation that you also have for a diatomic molecule. Only that in this case, we are not interested in the bound solutions of this Schrödinger equation, meaning the bound states of this molecular system, but in the scattering states, right? So those solutions with a positive energy. But otherwise, it's the same Schrödinger equation. So it has the general solution of this form. Yeah. So you again, so what you can do is you can separate the solution into two parts: an angular part, and the angular part turns out to be the Legendre polynomials as a function of cos theta because of the cylindrical symmetry of the problem, and the radial part, right? And now the interesting part of the solution is this radial part. We have again angular momentum. It's now quantized with quantum number 0, 1, 2, and so forth. Now we all know what Legendre polynomials look like. The interesting question is now, what do these radial functions look like? And if one solves the Schrödinger equation, then one finds as an asymptotic solution to these radial functions, these sort of sine functions. These are essentially the asymptotic form of Riccati-Bessel functions that one gets as a solution to this case. And I should say, we are only interested in asymptotic solutions here. Because, I mean, in a typical experiment, any detector that we use to detect the outcome of collision events is far away from the microscopic collision region where the two particles collide with one another. So what we essentially can measure is the wave function far away from the collision centers. And this is why we are only interested in the asymptotic form of the solution. And this is and this is the asymptotic form of the solutions that we get. So what we see here is that it's this sine function, right? And it has as arguments a term k times r. Yeah, and that is a bit reminiscent of what we also get for a free particle wave function. But then we have here two phase shifts, effectively. One of them is proportional to the angular momentum quantum number L. And it is actually a phase shift that arises because of the centrifugal term in the effective potential. And then we have another phase shift, eta L, and that is called the scattering phase. And this scattering phase is a phase shift in the wave function that arises because of the interaction potential B. Okay? So essentially what this means is that, yeah, I mean, the scattering manifests itself as phase shifts in the wave function. And it further turns out that it is this scattering phase shift which is then linked to the scattering cross-section. Now, the scattering cross-section can be formulated as something proportional to a sum over all angular momentum states times the sine squared of the scattering phase shift. So essentially, one needs to work out what the scattering phase shift is. And one can further show, yeah, and you can read this up, for instance, in this paper here, that in the semi-classical limit, meaning if we have large values for the angular momentum quantum number L, then the scattering phase shift can be approximated by this rather simple expression. So we assume that, again, that our interaction potential is an ion-induced dipole potential. So we only consider the C4 term in this multipole expansion. E is the collision energy, and L is the angular momentum quantum number. So, and if we have this expression for the phase shift, then based on this one can calculate a semi-classical expression for the scattering cross-section. And the important thing to realize here is that this in the end scales with the collision energy power -1/3. So we have an E power -1/3 dependence of the elastic scattering cross-section in the semi-classical limit. And what is shown here is the validity of this approximation actually as a function of the collision energy, that one can see that only at the lowest collision energy, where we only have few partial waves, meaning few angular momentum. So if the angular momentum of the collision is very low, then we have appreciable deviation of this semi-classical expression, which is the dashed line here, from a rigorous quantum solution of the whole problem. Yeah. So meaning, especially in the regime that we will be working, so that is millikelvins and above, typically for ion neutral interactions, we are still in the semi-classical limit with many partial waves. Okay, so I think this is a good time to ask questions. That is everything I wanted to recapitulate about ion neutral interactions and collision theory. Are there any questions at this point?
Stefan, yes, there's one question in the chat, which
Yes.
is, this expression is for elastic or total cross-section?
Elastic.
Right. Okay. I don't see any other questions. Maybe I can kind of talk to you later about this whole business, but carry on, please.
Yes. Okay. Good. Right. So let us now come to a few experiments. And I already said that I will focus in my talk on ion-atom hybrid systems. And so over the course of this school, you have heard about atom traps, ion traps, molecule traps. Now let's talk about hybrid traps. And a hybrid trap is a combination of an ion trap with an atom trap. And that is an experiment that has been originally proposed in a series of papers by Robin Coté and Winthrop Smith in the early 2000s. And they were first implemented, these sort of experiments were first implemented a bit more than 10 years ago, starting with a seminal paper by Vladan Willitsch's group in 2009. And where they combined a surface electrode ion trap with a magnetooptical trap. And since then, many different groups all over the world have come up with similar experiments. It's typically linear pole traps that are combined with magneto-optical traps, or linear pole traps with magnetic traps and or optical dipole traps, in which one can keep the atoms, and sometimes even in the form of a Bose-Einstein condensate. So this has now become a thriving field on its own. There are, I don't know, between 10 and 20 groups all over the world who have experiments like that, and there are many more groups who do theory on this kind of processes. So it's become a thriving business in itself. There are also already a range of review articles now on this topic, which I invite you to delve into if you're more interested in that. So to give you some ideas about what these experiments look like, let me say a few words about the experiment that we have in Basel. Our hybrid trap experiment consists of a linear radio frequency ion trap, very similar, completely the same actually as the ones that I have introduced in my first lecture. And that is superimposed with a magneto-optical trap. So a magneto-optical trap consisting of two coils that create an inhomogeneous magnetic field, quadrupolar magnetic field. We then have laser beams in an optical molasses configuration, which then cool atoms in this quadrupolar magnetic field. And in our case, it's rubidium atoms, which are kept in this mod. You see here a fluorescence image of these rubidium atoms, which are kept in the mod and superimposed with the ions. And on the ion side, we have calcium ions. Sometimes we also have barium ions, which are laser cooled in here. But then we can also load molecular ions into this trap to look at molecular processes, and this is what what I will be talking about at the end of my lecture. Okay, so I would now like to talk about a few examples of processes that one can study in these experiments. And what it turned out is that there's a rich collision physics, right, and also chemistry, as a matter of fact, that one can observe in these experiments. So let's start with a few simple things, right? Let's talk about elastic collisions between the ions and the atoms in such an experiment. And this is one of the very first results that came out of this field from Johannes Eckardt-Enschlag's group in Ulm, where they had where they have an experiment where they trap barium ions together with rubidium atoms. And of course, what the simplest types of collisions that can happen here are elastic collisions. And this is what they have been studying here. Yeah, what we see here is the number of atoms that are held in an ultracloud in a cloud of ultracold atoms that is superimposed with in this case it was a single barium ion. And one can then see that the number of atoms decreases as a function of the interaction time with this barium ion. So what happens here is that we have collisions between the atoms and the ion in the trap. And the atoms are usually much colder than the ions in the trap. And moreover, the ions, they also have micromotion. We have already briefly touched upon this last time. This is this fast oscillating motion that an ion assumes in an RF trap. Yeah, and so the ion is more energetic than the atoms. And by elastic collisions between the two, the ion can impart then kinetic energy to the atom with which it collides. And these atom traps, they are usually not too deep, right? So if the atoms are too energetic, they fall out of the trap. And this is what we are seeing here. And so what they have done is they have moved the ion in space through the atom cloud. And depending on what sort of atom cloud they had, either a thermal cloud or a partially condensed cloud or a fully Bose-Einstein condensed cloud, then they could essentially map out the density profile of this atom cloud by just looking at the loss of the atoms through the collisions with the ions in this trap. Okay, so this is elastic collisions going on, which essentially lead to an ejection of the atoms from the atom cloud. What this can actually be used for is to minimize the micromotion of the ions, right? I mean, if you minimize the atom loss, when you overlay the atom with the ion, then as a function of the ion position, you can use this to try to place your ion on the RF null line of the trap, where the micromotion is ideally zero, and in this case, minimize the micromotion, excess micromotion in the system. And that is shown, for instance, in this paper. Okay. So these elastic collisions, they can also be used for sympathetic cooling of the ions by the atoms, because what these atoms are, they are nothing else than a buffer gas, a cold buffer gas, right, in which you immerse a typically hotter ion. Okay, so by collisions of the cold buffer gas with the ions, you can, you can cool the ions. And that is shown here in this work by Michael Köhl's group from a bit more than 10 years ago, where they determined the ion temperature as a function of the interaction time. In their case, it was ytterbium ions with ultra-cold rubidium atoms. And as a function of the interaction time, they saw that the ion temperature decreases. And because of sympathetic cooling of the ions by the atoms. Buffer gets cooled, if you like. It's nothing else than that. Okay, so that are simple elastic collision processes that can happen here, right? You can use these ultra-cold atoms to cool the ions, yeah, and you can also use the ions to eject atoms from the trap by elastic collisions. Now let's look at a bit more, yeah, let's say more gory phenomena. And it turned out that in this variety of different ion atom hybrid systems that have been implemented over the last decade or so, maybe not to everyone's delight, it turned out that in many of these systems actually a very rich chemistry happens. So we not only have elastic collisions or maybe inelastic collisions, but we really also have reactive collisions going on here. And moreover, it turned out that what is very important is the role of light in these experiments. Because, yeah, I mean, the ions are very often laser cooled in these experiments, or they are laser cooled to start with for sure, but also during the operation of the experiment. The atoms are laser cooled if it is a MOT experiment. So photons are always present, right? And therefore excited states of both the ions and the atoms are present. And this turned out to play an important role in many cases. So I'd now like to start this topic with presenting a few results from our group. From predominantly on the calcium rubidium system. And this is a typical scenario that you have in our experiment in Basel. So we have a calcium Coulomb crystal that is immersed in a cloud of ultra-cold rubidium atoms in the MOT. And what you can already see from this image here, so you see both particles are fluorescing. So this means both of them are laser cooled, right? So both the ions and the atoms are laser cooled, and therefore there's always population of both the ions and the atoms present in the excited states. So what we then saw in the very first experiments that we did, and this was now also about 10 years ago, we saw that the calcium ions would disappear from the trap as a function of time. And so this is shown in this image here. So this is just focuses on the fluorescence of the calcium ions. And one can see that this calcium Coulomb crystal shrinks in size over the time scale of a few minutes. And one can further see that this crystal gets characteristically flattened. And this flattening essentially is caused, as we've already discussed in my first lecture, is caused by the sympathetic cooling of molecular ions or other ions, non-fluorescing ions, I should say, which are formed by this process. The interesting question is now, of course, okay, this is clearly some reactive processes that's going on, right? I mean, the calcium ions, they are transformed into another chemical entity, whatever it may be. So the first question, of course, is what is this chemical entity? And one can now do is one can turn the ion trap into a mass spectrometer in a very similar way as we have already discussed in my first lecture. So one can apply a small tickle voltage to an electrode in the ion trap to resonantly excite the ions in the trap. So scan the frequency of this tickle voltage and then map out resonant excitation of the ions, which depend on the mass of the ions in the trap. So in this way, you can take a mass spectrum of the species in your trap. And this is shown here. So before the reaction, we just see a single resonance, and this corresponds to the calcium ions, which are present in the beginning of the experiment. But then in the end, we take a mass spectrum, which looks like this. And this has now 4 peaks. And we identified these 4 peaks with the emergence of, well, there are still a few calcium ions left, but we have 3 more species that emerged over the course of these collisions. And we attribute them to rubidium 2+, calcium rubidium+, and also rubidium+. Now, how on earth can one get these sort of species here? And for this, one now needs to turn to theory and look at what can actually happen during these collisions. And what you see here are potential energy curves, so the interaction potential between the collision partners for various states of the collision partners. So we have rubidium in its ground state and calcium ions in its ground state. Yeah, so this is the lowest collision channel that we can have if both particles are in the ground state. And associated with that, we have that sort of interaction potential, right, which is this thick red line. However, what one has to realize is that this here is not the lowest state of the collision system. Yeah, rubidium has a lower ionization energy than calcium, right? So this means that there are charge transfer states which have a lower energy than our entrance state. Yeah, so these are states where the charge has hopped over from calcium to rubidium, or an electron has hopped over from rubidium to calcium plus, if you like, and they are lower in energy, right? So this, the absolute ground state, is where we have a rubidium plus ion and calcium, neutral calcium atoms in their ground state. And then there is still another asymptote below our entrance channel, and this is where the calcium has been excited, or one electron in calcium has been excited to the 4p orbital. So, and with every one of these asymptotes, we have, of course, molecular states associated with them, right? And these molecular states, they go along with their own potential energy curves, as one can see here. And during the simplest case of the collision that we can have, right, where the rubidium atoms and the calcium ions in their ground state collide with one another. So then during the collision, we come in here, right? As a function of the internuclear distance, those two come close to one another. And at some point, they reach a region where we have a crossing with this green dashed curve here. And that is a potential energy curve that is associated with this charge transfer state. And whenever we have a crossing between potential energy curves, right, then this is a region with an increased degree of interaction between the states. These are so-called non-adiabatic interactions. And through these interactions, the collision system can hop over from one curve to the other. Yeah. And if it hops over to the green curve, right, then after the collision, the 2 particles can depart again on the green curve and then arrive at this asymptote. Yeah. And there you see at this asymptote, we had a charge transfer, right? So, and this explains in part the observation of these rubidium ions in the trap. But there is more. We also have, we can also have radiative processes, right? I mean, this is an excited state, right? And during the collision, in principle, a photon can be emitted, right, down to the lowest curve. And depending on whether a bound molecular state on the lowest potential energy curve is populated, or if a scattering state is populated associated with this lowest energy curve, we have either radiative association, so the formation of molecules, or we have radiative charge transfer. Yeah, so if you populate a scattering state, then the system is not bound, right? So the particles can depart again and again reach this asymptote. So we have rubidium plus again, right? And if a bound state is populated, well, then we have a bound molecule, and that then leads to the formation of calcium rubidium plus. Okay, and the rubidium 2 plus that we also observe in this experiment are most likely due to a chemical process where this calcium rubidium plus further reacts with rubidium atoms in the trap. Okay, so we have 3 processes that can go on here in principle: non-radiative charge transfer at these curve crossings, radiative charge transfer, and radiative association. Okay, so this is a rich physics that's going on, if you like. One can now also, ask further questions. For instance, what is the rate constant associated with all these processes, and in particular, what are the rate constants of the different collision channels that we have? I mean, we have collisions between ground state calcium plus and ground state rubidium, which is what I've just discussed. But then we also have collisions with excited state calcium and rubidium. And we can also have in calcium, we have two excited states present. Actually, we also have this double D3 half state, right, which is also partially populated in the experiments. So, and what we now asked in these studies is, okay, what is the rate constant associated with collisions of ground state rubidium with calcium plus in any one of these three states? And it turned out that collisions with calcium ions in this excited P state are clearly the fastest, right? By more than 2 orders of magnitude compared to collisions in these other two states. Now, why is that? Why do we have such a pronounced state dependence of the rate constants of these collisions? So a qualitative explanation for this can be gleaned from the full, well, it's actually not even full, but from a fuller potential energy diagram of this collision system. So here on the lower part, these are the potential curves that I have showed you before, right? But there are many more if you increase the energy, right? And here, what you see here is the asymptote rubidium in its ground state with calcium plus in its 4p state, which corresponds to this rate constant here. And you see that below this asymptote, right, you have many, many more asymptotes, right? And moreover, what I show you here in this part of the figure are only the states of singlet sigma symmetry, molecular states of singlet sigma symmetry. There are triplets, there are pi's, there are delta states, right? So if I would plot them all, right, there would not be much white left on this plot. So this is a very dense energy level structure that we have in these collision systems. And what one can already glean from looking at this here is that we have if we have a collision on this curve here, if the two come together, then we have many crossing points. In this case, they are drawn as avoided crossings with other molecular states, which give multiple opportunities for non-adiabatic charge transfer. And of course, still, I mean, there can also still be radiative processes, and you can radiate down to a variety of different states down here. So there are also many opportunities for radiative association and radiative charge transfer. And so working this out qualitatively from theory is extremely challenging. It has not been done, but just from a qualitative picture that we get here is that the number of possible reactive channels, right, in collisions in excited states is very high, and this is probably the reason why we observe such a considerably larger rate constant in the excited channels compared to the lowest channel. Okay, so another interesting question that one can ask now is, okay, so what is the collision energy dependence of these processes? And so we measure now these rate constants as a function of the collision energy. And what you see here, let's just focus on calcium plus rubidium again, is now a channel averaged rate constant, so averaged over all these collision channels, as a function of the average collision energy from about 10 millikelvin up to about 10 Kelvin. And one can see this is essentially flat. So a few words on how we tuned the collision energies in these experiments. What we did is we essentially imparted a well-defined degree of micromotion to the ions, right? And so we essentially we pulled them off the RF null line to give them excess micromotion, and so that the average collision energy is determined as a matter of fact by the average micromotion energy of the ion. Okay, and we did a similar experiment for barium plus rubidium and observed a very similar result here. So And what one can see here is this, okay, the collision, the rate constant is essentially constant with collision energy for both of these systems. And this is a bit reminiscent of what one gets from Langevin theory. Okay, Langevin theory predicts an energy independent and therefore temperature independent rate constant. The magnitude of the rate constant is smaller than the Langevin rate constant. It's important to realize here, but the energy dependence is very reminiscent of what we get with Langevin theory. So how can one understand this? And one can understand this if one looks a bit closer into the quantum mechanics of these different processes that we are dealing with here. So radiative charge transfer, radiativization, and non-radiative charge transfer. So it can be shown that the cross sections for these processes, and this is essentially discussed in this seminal paper by Alex Daldano and Siegelman here, can be cast in expressions like this. Yeah. I don't want to go into too many details here. Suffice to say is that the cross section is essentially given by a sum over all angular momentum quantum numbers that we have here. Then we have an integral over all, so for radiative charge transfer now, we have an integral over all final energies of the charge transfer products. Then we have an omega power 3 term, right? This is a bit reminiscent of what you have also in the Einstein A coefficient. So there is an omega power 3 dependence, and omega is the angular frequency of the photon that's emitted. So it's the same as we have in an Einstein A coefficient. But then we also have this transition dipole moment matrix elements. Okay, so this is essentially the dipole moment matrix element for the optical transition between the initial state and the final state. Right? Remember, these are radiative processes. Okay, and for radiative association, we have analogous expressions. Okay, so but the important point is here that we have these transition dipole moments that play a role here. And for non-radiative charge transfer, we have an expression. And here the important point are these non-adiabatic transition probabilities, right? That happens at the curve crossings between two molecular states. And at these points, as I've already mentioned, this is where the transition from one curve to the other predominantly happens. Okay, so now let's focus on these radiative processes, and a similar argument can also be made then for the non-radiative charge transfer processes. So what one realizes with the example of calcium plus rubidium is that that these transition dipole moments, right, which drive the radiative transitions, they are all localized at short range, okay, because the wave functions need to properly overlap of the initial state and the final state, right? And they do this best at short range. And what I show you here in the upper part of this plot is the value of these transition dipole moments, right, for radiative transitions in calcium rubidium that we have discussed before. And let's focus on this red thick curve, right? That is the transition dipole moment for a transition from our entrance channel, calcium plus in the ground state plus rubidium in the ground state, colliding with one another, and then radiating down to the absolute ground state of the system, which is rubidium plus calcium. Okay, and so you see these transition dipole moments, they only become appreciably large at short internuclear distances. So in the lower part, I show you again the potential energy curves, right? It's the same ones that I have showed you before. So we come in here on these potential energy curves. Here we have crossing points with another state. Here non-adiabatic charge transfer can happen. And here at close internuclear distances where these transition dipole moments become large, we can then have radiative transition down to the absolute ground state. Now, you realize that in the region where these transition dipole moments are large, we have the potentials associated, or I should say the potential, we are already deep in the potential well associated with this, with our entrance channel. Okay, so this can't be seen here on this scale, but the well depth here is on the order of 1000 Kelvin. Okay, so meaning when these radiative processes kick in, our two collision partners are already sufficiently close so that they are around the region of the bottom of this well, at which point they already have been appreciably accelerated by this interaction potential. So we come in here at very low collision energies, 10 millikelvin, 100 millikelvin, 1 Kelvin or so. But classically, what happens is that the closer they get is, then this potential starts to accelerate them, right? And then they come to close internuclear distances, and then they can either undergo non-adiabatic charge transfer or these radiative processes. But locally here, they have become fast. Yeah. So meaning the curvature, let's put it in other words, the curvature of the wave function in here, right, is predominantly determined, right, by the depth of this well, right, and not by the asymptotic collision energy anymore. So meaning that whenever we have the case that we have an appreciably deep potential energy well, right, out in the region of which these reactive processes happen, then it doesn't really matter whether the asymptotic collision energy was 10 millikelvin, 1 Kelvin, or 10 Kelvin, right, if the well depth here is 1,000 Kelvin. Okay, so because the properties of the wave function will then mostly be determined by the depth of this well, and that explains the insensitivity of the cross sections and the rate constants, or I should say the rate constants, to the asymptotic collision energy that we observe in these systems, and this is also very nicely reproduced by rigorous quantum calculations of these processes. Okay, good. Yeah, I would say let's take a few questions at this point. So
right.
A good place to stop.
Yeah. Yes, Stefan, there are a couple of questions. So the thing is, how do you measure elastic collision cross sections in the experiments? And how do you differentiate it from non-elastic cross sections in experiments?
Yeah, that's a very good point. So in the experiments on the elastic collisions that I have shown, right, the elastic collisions have been traced by the disappearance of the atoms from the track. Yeah, but you know, in principle, also inelastic processes can have state-changing collisions. Yeah, which affect the ion and which you would not notice if you didn't probe the ion explicitly. Now, whether this can happen or not is determined by the structure of the ion, of course, and by the energy available, whether such inelastic processes can happen or not under the conditions of the present experiment. Yeah. But it's a good point. I mean, yeah, one always has to be careful that maybe not also inelastic processes can happen as well. So if you have reactive processes, right, like I was talking about on the last slides, I mean, then it's rather simple, yeah, because I mean, if you have a chemical reaction going on, right, then you see a chemical change in your ions, right, and then it's clear it has to be a reactive process.
There's another question: would you need C3 term in the multipole expansion to get collision rates for P and D levels?
Sorry, say again.
Would you need C3 terms?
Yeah.
In the multipole expansion to get the collision rates for P and D levels?
Yes.
Right. So
yeah, I will come back to that later, actually. But yeah, okay. Let me qualify this remark a bit. It depends on the collision energy. Yeah. They become important only, or you notice them in the experiment only at very low collision energies. And at high collision energies, they actually do not manifest themselves that strongly in rate constants. Yeah. So whether you have to include them or not depends on the specific of your experiment. But in principle, they are there, right? I mean, if you have an ion interacting with a neutral particle, with a neutral atom, right, in a non-S state, then you have these three terms in principle.
Right. We are.
Unless you are in a J equals 1/2 state.
Yeah, I think we can move on.
Yeah.
Yeah.
Okay, shall I carry on, or are there more questions?
Not at the moment.
Not at the moment. Okay, good. So these excited state processes that I have been talking about, which are very important in experiments when we have light present that excites the particles to excited states, either the ions or the atoms. They are suppressed in certain cases. And one of these cases is, for instance, the calcium ytterbium plus system that has been studied in Eric Hudson's group. And in the following way. Now, whether such a radiative charge transfer process or radiative association process happens is, it's of course important that the two collision partners come close enough, right? So that that for instance, a bound state on the lowest potential energy surface can be populated. Now it happens that in some systems, like calcium ytterbium plus, we have a situation where the excited states are very short-lived. Yeah, in the sense that the excitation decays already before the partners can come close to one another. And in this case, the rate constants for the processes out of these excited channels, they are very low or even negligible. So what one can now do, both to prove this and play around with this a bit, is one can apply an additional laser beam, right? Which is not like the MOT laser beams that one has already in the experiment, but an additional laser beam, which is a bit detuned from the usual MOT transition, say, to excite then the system, not here in the asymptotic region, but already further inwards when the two collision partners have come closer together. And the calcium ytterbium plus, one also has a situation where one has non-adiabatic charge transfer at short internuclear distances. And this non-adiabatic charge transfer is usually not seen in normal experiments without this catalyzed laser, because the excitation that one needs in order to access this region of non-adiabatic couplings is decays before the two collision partners can come close enough so that this non-adiabatic charge transfer can kick in. But what can one do is one can now insert another laser beam that excites the system just at the point before the two particles come close to this region, thereby populate this excited state, come close again to this to this non-adiabatic coupling region at which this charge exchange can happen. And then from this curve, which is populated in the experiment, right? This is this orange curve. Charge exchange can happen again, right? And then the system can then, or the two particles can depart again after hopping over to this red dashed curve to this asymptote here, which is again a charge transfer asymptote. So, and what is shown here is a result, right? So this shows the rate constant measured in the experiment for this charge transfer as a function of the detuning of this catalyst laser. And here one sees the situation without any catalyst laser. Yeah, so one measures a rather small rate constant. But then if this catalyst laser is switched on, one sees a marked decrease in this charge transfer rate constant as a consequence of the presence of this catalyst laser and the population of this excited curve during the collision. So I think this is it's a fun experiment which shows how one can play with these excited state processes and how they manifest themselves in different ways in different systems. Okay, so another topic related to this charge transfer processes is the phenomenon of swap cooling. And that is quite an intriguing cooling mechanism of ions that can happen in hybrid traps, which has first been, I would say, discovered and also explored by our chairman, Sadiq Rangwala, now also almost 10 years ago. And so the mechanism is as follows. So if you have a homogeneous hybrid system, so meaning ions and atoms of the same chemical species, say rubidium, and if you have, say, a fast ion, right, that collides with a slow atom, be it in a motor or in another atom thread, then what you can have is when those two come close to one another, you can have a resonant charge exchange, right, which is very efficient. So essentially, the charge hops over from the fast ion, right, to the slow atom, and the slow atom becomes then a slow ion, right? And the original fast ion becomes a fast atom. Yeah. So in this way, you are left with the same ion species again, yeah, but now it's considerably slower. And that has been worked out in this paper by Sadiq's group already, yeah, in 2012. And I should also mention there is a nice experiment from Johannes Heckadenschlag's group very recently, where they also characterize these sort of processes in detail experimentally. So, and also quite an interesting phenomenon that can happen in these hybrid traps when you have very dense clouds of neutral particles is three-body processes. And that has been explored in quite some detail in Johannes Heckadenschlag's group in Ulm, in experiments where they looked at both rubidium plus and barium plus ions in ultracold rubidium clouds. And what they saw is essentially that if the atom clouds are dense enough, right, so close to a Bose-Einstein condensate or even a Bose-Einstein condensate, then one can have three-body recombination. Yeah. So in a way, you can think of it as the ion present in this experiment acting as a catalyst to form a rubidium-2 molecule, right? So in a three-body collision, we can form a bound molecule out of two ultracold rubidium atoms, and the excess energy, the binding energy or parts of the binding energy that is released in these three-body collisions is then taken up by the rubidium ion. Yeah. And they explored this both as a function of the density of the atom cloud, and one can see that in order to get an appreciable free-body association probability, one needs rather dense atom clouds, yeah, much denser than one usually gets in a MOT. And moreover, what one needs is rather cold, rather low collision energies. And so this only works at very low, at very low energetic conditions. So otherwise, the molecules that are formed are not stable. Okay. That brings me to my next topic now, which is also associated with these different collisional processes in the traps. And that is the question, how well does this cooling that one sees of the ions by the ultracold atoms really work? Or in other words, are there any limits to this sympathetic cooling that is exerted by the ultracold atoms on the ions? And that is, of course, an interesting and relevant question, because cooling of ions, is a topic with a long history. And as I've already said, one cannot laser cool everything. And so if one has a general method to cool ions down to very low temperatures, in particular a prospect of reaching ultra-cold temperatures, then this would of course be a great thing, right? And in the beginning of this field, there were great hopes that one could use these ultra-cold buffer gases, right, to really prepare ultra-cold ions or different species of ultra-cold ions just by buffer gas copy. Now it turned out that there are, things are always not that easy. And it turned out that there are some very stringent limits to the sympathetic cooling that one can reach here. And the problem is very so often with trapped ions is the micromotion. So we've encountered the problem of, or the phenomenon of micromotion already several times. So let me just briefly remind you what this is all about. So we have an ion in the RF trap, right? And you can decompose the motion of such an ion in the RF trap into two components. Secular motion, that is essentially, you can think of this as the thermal motion of the ions in the effective potential of the ion trap, but superimposed on that, you have the micromotion. This is a fast oscillating motion which is driven by the RF fields. And this here, to illustrate this here shows a trajectory of such an ion, a phase space diagram of such an ion in an RF trap, simulated trajectory. So the dashed red line would be the ion trajectory without the micromotion. So this would correspond to the secular motion in the time averaged effective potential of the trap. And the red and the blue trajectory is the same ion, but now with the micromotion in the full time-dependent potential of the ion trap. And one can see the effect of this micromotion the further one gets away from the trap center, where the RF fields vanish for symmetry reason. The larger the micromotion gets, the larger the amplitude of the micromotion gets, and therefore also the larger the energy stored in the micromotion gets. So, and what one typically does in ion trapping experiments is one tries to minimize this micromotion as much as one can, meaning put the ions into the center of the trap onto the RF null line, where ideally the micromotion vanishes. So even if one manages to do that, right, as good as one can reasonably do, then in such a hybrid trapping experiment, there is still a complication there. So the micromotion still starts to play a role because, and this has been first discussed in this seminal paper from Vladan Willitsch's group, that even if the ion is placed on the RF null line, right, at the point when some neutral particle approaches the ion, right, then the interaction between these two particles starts to pull away the ion from the RF null line. Right, and in that case, it assumes micromotion again, even if the micromotion was perfectly compensated to begin with. And if then a collision happens, right, under conditions where we have micromotion, then in unfavorable circumstances, right, through the collision, micromotion energy is then coupled into the secular motion, and that then leads up to a heating of the ions. And of course, how big a problem that is, that depends on when in the RF cycle, when in the micromotion cycle the collision really happens, right? But if you average this over time, right, it turns out that you cannot really neglect this. Yeah. So that means that even, right, if you have perfectly cold, perfectly micromotion compensated ions, even if we have cooled them down to the motional ground state of the trap, and even if we have ultra-cold atoms, right, and this means that through these collisions, and if these collisions are elastic, and if you already have a couple of them, then you get the heating of the ions because of micromotion interruption. And it's first been discussed in this paper, and it actually then goes back to problems that have been known for a very long time. Namely, that this micromotion heating, or the degree of heating by this micromotion, also depends on the mass ratio of the buffer gas to the ion. Yeah, and that has first been discussed in this seminal paper by Hans Dehmelt already in the 1960s. That where it was explained that the buffer gas should not be too heavy. Yeah. So meaning the ideal situation is if you have a light buffer gas and the heavy ion, then this problem of micromotion heating of the ions through the collisions is not a problem actually, or a lesser problem, and you can still get efficient buffer gas cooling. But if under conditions where the buffer gas is heavier than the ions, then you essentially don't get cooling, but in many cases you can get heating. And that is also shown here in this plot here, where we have performed the simulation of a cold ion in a radio frequency trap, and just looking at 25 ion neutral collisions with a buffer gas, which was assumed to be in the simulations at 0 Kelvin for different mass ratios. And we were looking at the distribution of ion energies after 25 such collisions. And that one can see that as a function of the neutral to ion mass ratio, right? So for the distribution gets ever broader after these 25 collisions. So the heavier the neutral compared to the ion, right? So the broader the energy distribution of the ion gets after these collisions, even if we start with very cold ions and very cold atoms. And the reason is just this coupling of micromotion energy into the secular motion of the ion. So all of this needs to be qualified a bit, right? Because it also turned out that the degree of heating and cooling is also sensitively dependent on the shape of the ultracold atom cloud. And the first one to point this out was actually also again our chairman Sadik in this paper from a few years ago, where it was essentially shown that if you have a localized atom cloud, right, say in a MOT, right, and if you have an ion whose initial trajectory is much larger than the extent of this atom cloud, then you can still get buffer gas cooling, even though the buffer gas is much heavier than your ion. Yeah, so these are localization effects that also play an important role here. Okay, so that has become a big topic in recent years in the field. And one experiment to first explore these kind of phenomena really in the ultracold regime is this seminal work from Roy Ozeri's group, which was the first hybrid trap experiment where they really managed to combine ground state cooled ions, so ions which have been cooled down to the motional ground state of the ion trap, with ultracold atoms. And in this experiment, they had strontium ions paired with ultracold rubidium atoms, and they were cooling down the strontium ions to the ground state of the trap, and then looked at collisions of this ground state cooled ions with the rubidium atoms in the trap. And we're then exploring the energetics of these collisions and the ion energy distributions. So what it turns out is that the energy distribution that the ion assumes because of this micromotion heating during the collisions, these are not thermal distributions, right? Because it's not a system in thermal equilibrium, right? The system is always driven by the RF fields. So it's non-equilibrium thermodynamics that we are talking about here. And it turns out that the ion energy distributions that one gets here, that they can be understood in terms of a so-called Zallis distribution. Yeah, Zallis distribution, this is a generalized distribution which can be written down in different ways. One is given here from this paper. And so these are energy distributions that one gets for non-equilibrium systems, which under certain conditions can then assume the form of Boltzmann distributions again. But whenever one has such Zallis distributions, it's an indication that one is not really in thermal equilibrium. And a few years ago, we also showed that one can, starting from some very fundamental considerations, can prove that for the case of an ion atom hybrid system in an RF trap, we really have to arrive at something like a Thales distribution. Okay, so what they then did is in this experiment, they had this strontium ion in the trap, in the ground state, and then interacted with the ultracold rubidium atoms. And after a few collisions of an ion with atoms from the ultracold rubidium cloud, they would then determine temperature is a bad word here to use, but they would essentially map out the energy distribution, the kinetic energy distribution of the ion in the trap. And they were doing this by Rabi thermometry on a quadrupole transition in the strontium ion. So essentially the same type of thermometry technique that I was also already explaining in my first lecture, which, for instance, we used in our own group for measuring coherent motion excitation of calcium nitrogen ion strings, right? So these were spectroscopic experiments done in the resolved sideband regime, and they were looking at sideband transitions of this ion on these narrow transitions, and they were driving Rabi oscillations, and from the amplitude and the frequency of these Rabi oscillations, they could then essentially work out the ion energy distributions in the trap after collisions with the ultracold rubidium atoms. And these were typical results that they got. You see, this was a typical Rabi oscillation for an ultracold ion before the collisions, and this is what they got after the collisions in the different sorts of experiments. And then they were modeling these Rabi oscillations, first assuming just a thermal distribution of the ion energies in the trap, and then a Thales distribution. And one can see that the Thales distribution fits the data much better than the thermal distribution. So this already suggests that these ions that are after the collision is not thermally distributed, right? But it's a non-thermal distribution which can be well modeled with the Thales distribution. And they were then determining ion temperature as a function of the number of collisions that they had between the ions and the atoms in the trap. And what they found out through all these experiments is that even if they start with the perfectly ground state cooled ions and with ultra-cold atoms in the trap, in the end, what they arrived at is that the steady state temperature of the ion in the trap after all these collisions was not what corresponds to the ground state of the ion in the trap, but to about 7 millikelvin. Yeah, so it's quite high. And the reason was this effect. This was this micromotion heating of the coupling of micromotion energy into the secular motion because of collisions between the two species during the micromotion cycle, when the ions were pulled away from the RF null line through the interactions with the ultra-cold atoms. Okay, just to briefly wrap this up, let me mention a very recent experiment where they tried to circumvent this problem by choosing a very light buffer gas and a very heavy ion, lithium and terbium. And this is an experiment from René Herritzma's group in Amsterdam. And the objective here was really, okay, we really want to study ultra-cold collisions now. Yeah, so collisions where we only have a few partial waves left, yeah, where we are not in the classical regime anymore, but where we really want to see quantum signatures in the collision. And one big obstacle for reaching this regime was exactly this micromotion. So they implemented an experiment with a very light buffer gas and a very heavy ion, right, where these problems are minimized. And by doing so, they achieved exactly that. And this was really, to the best of my knowledge, the first experiment where they could see an ion-atom collision process close to the single partial wave regime. where in their case they looked at the spin flip process in the ytterbium ion, where they could really see a non-constant spin flip probability, which is attributed or was attributed to quantum features in the collision, right? In this case, so-called resonances, right, which modulate the spin flip cross section at certain collision energies, right? So this is a very nice experiment, a heroic feat, if one can say, where they really managed to drive ion-atom collisions to very low energies and start seeing quantum features in ion-atom collisions. Okay, so I think my time is already up. I will therefore skip the very last part of my lecture and stop here. And I don't know, Sadik, do we have time for one or two questions still?
Right now, there are no questions on the panel. So if you want to take a couple of minutes to go through this, it's okay, I suppose, or I can ask you many questions and fill the time. You could just continue and give people, because there's nothing in the chat, Stefan.
Okay, good. So let me then maybe take 5 more minutes or so and
that's
talk a
okay.
bit about molecular effects. And this also then will allow me to go back to one of the previous questions. So how do these C3 terms manifest themselves in these experiments? Shall we do that?
Yes, yes.
Yeah, okay, very good. So just very quickly and very briefly, all of the experiments that I have been talking about so far were dealing with atomic ions and ultracold atoms. And a couple of years ago, we and then also other groups, we started to introduce sympathetically cooled molecular ions into these hybrid trap experiments. And so let me just show you a few results and phenomena that one can observe here. So specifically what we had been looking at is charge transfer dynamics, now including molecular ions like N2 plus and O2 plus with the ultracold rubidium atoms. And again, what is important here is the N2 plus and the O2 plus molecular ions, they were sympathetically cooled in our experiments. And they were all always in the ground state, in the electronic ground state, but the rubidium atoms, they were in a MOT in our experiment. So we again had collisions in the ground state and in the excited state. Okay, so we now also did a slight upgrade to our experiment in order to be able to be more precisely tune collision energies, right? Because we've already seen the collision energy dependence of these processes is a very important is of large interest in this whole discussion. And what it is, we came up with what we call a dynamic ion-atom hybrid trap, where we did not overlap the MOT with the ions in the center directly, but we produced the MOT off-site, the ions, and then we used the laser beam to exert radiation pressure on the ultra-cold atom cloud to push them through the ions and recapture the atoms on the other side. And then we were pushing them back and forth, right, at well-defined velocities. And in this way, and by changing the intensity of this push laser beam, we could accelerate the atoms to different extent and therefore precisely tune the collision energies in these experiments. And this is a much more precise way than tuning collision energy by just imparting micromotion on the ions. Okay, so this is a movie which shows this atom cloud flying back and forth between the two extreme positions in the trap. So let me just quickly tell you a few of the phenomena that we see here. Let's focus on the case of N2 plus rubidium. So the process that we are looking at is N2 plus colliding with rubidium, either in its ground state or in the excited doublet P3 half state. And the product of this collision is then a rubidium plus ion, so it's a charge transfer, right? Plus nitrogen in some excited electronic state. And it's important to realize that nitrogen and rubidium have vastly different ionization energies. So the energy liberated by this charge transfer is quite high, right? You can see it's on the order of 100,000 centimeters to the -1 or 13 eV, whatever you prefer. And so we produce nitrogen in highly excited electronic states in that way. What we are now measuring was charge transfer rate constants for this process, both with rubidium in the ground state and with rubidium in the excited state. And what we saw here also was that there's a massive difference, right, in the rate constants between collisions with rubidium in the ground state and with rubidium in the excited state as a function of the collision energy, and also the energy difference seems to be quite different. Now, what is the reason for that? Let's have a look at the process in the excited state first. So here the rubidium is in a doublet P3 half state, right? So this means this can't be viewed as a structureless particle anymore, but it is because we have one electron in the p orbital. So the valence electron is in the p orbital, so this is not spherically symmetric anymore. So this means that we do have a permanent quadrupole moment in this state. And that means we have a C3 coefficient, right, in the interaction potential. And this manifests itself in the rate constant. The rate constant that we measure is on the order of 2 × 10⁻⁸ cubic centimeters per second. And the Langevin rate constant is a factor of 4 lower, right? So we have a process that is considerably faster than Langevin. So we have to take into account this C3 coefficient now. And one can then predict the classical capture rate constant as a function of the collision energy, right? Taking into account the C3 term. And one can see that in the Langevin case, only the C4 term, we have a rate constant that is constant with the collision energy, but including the C3 term, we now have a rate constant that strongly depends on the collision energy. And at room temperature, right, say, or collision energies that correspond to room temperature, there is little difference between them, but at 20 millikelvin or so, where we were in this experiment, right, there is really this factor of 4 difference. And this is a comparison with the experiment, and you can see that it agrees very well. So at these low collision energies, this 3 coefficient really becomes important. So in the ground state, with rubidium in the ground state, we have a rate constant that is slower than Langevin, right? Lower than Langevin by a factor of 3, right? So this means that it can't really be understood in terms of capture dynamics anymore, but we have to also look at the short range part of the collision, right? What happens at short range in order to understand what's going on. And so we did this through some rather extensive theoretical modeling together with colleagues from theory. And at this case, one really has to start looking at the potential energy curves again and how these states interact with one another. And it turns out that with N2++ rubidium in the ground state, we have the case where we come in on this red potential curve, right? And then it turns out that this curve intersects with a charge transfer state. And around these intersection points, again, we can have non-adiabatic charge transfer. However, what becomes important here compared to the atomic collision system is now that we also have an orientation dependence, right? Namely, how the rubidium atom is oriented with respect to the nitrogen molecule when the two approach one another. And one can see that the couplings between these curves is strongly dependent on the orientation angle between those two, between the two collision partners. So to cut this long story short, what one gets out of this is that the collision dynamics is in fact rather complex. And what goes on here is that if the two collide with one another, they enter on the red curve, right? And then they can be trapped in this potential well for some time. And during the time they are trapped here, they can undergo multiple collisions or multiple crossings between the two curves. And only if they find themselves at the crossing on the black curve on an outgoing trajectory, then they can undergo a real charge transfer, right? And the probability for this is not 100%, and therefore we in the end observe a rate constant that is lower than Langevin. Okay, so this means that in these molecular systems, short range effects also become very important then. So I already see Sourav becoming restless because I'm taking up too much time. I think I'll stop here.
So yeah, thank you very much, Stefan. It was a lovely set of lectures. And on behalf of everyone, I give you applause.
Thank you very much.
Everybody else is muted, so, you know.
Yeah. Thank you very much. So it was a great pleasure to be here.
Yes, Stefan. And stay safe and see you soon.
And same to you. I wish you all the best, an interesting school, and I also wish you best of luck in this difficult time in India at the moment. Thank you very much.
Okay, then. Bye.
Bye-bye.
Okay. Yeah, thank you.
Hey, Markus, how are you?
Hello. Hello, Manas.
Hello.
Hey, Markus.
Hi. Good, perfect. Good to see you.
Sourav, we have 5 minutes, is that correct?
Mm-hmm.
Yeah, about three, yeah, maybe about 5 minutes. It says
Okay.
3. But you are not the co-host, it seems. Are you? Can you?
I can still unmute myself, and that's good enough, I guess.
Okay. So, but whether the slide sharing is working is.
I'll test now.
Just check if it's working.
It's coming up. Yeah.
Yeah, it seems to be.
Everything there?
Yeah,
perfect.
yeah.
Good. Audio is also fine?
Audio is also fine. Yeah,
fine.
yeah.
Perfect. Good.
I mean, for me, yesterday it was okay. I think I got from the organizers that they had issues with hearing it.
I mean, you should mention if there's something problem,
I think it's
because
okay.
I cannot hear myself. Of course.
Right. You know, there is famous story from NUS that someone lectured for 2 hours without realizing that he was muted.
Oops. Okay. Well, that's a good one.
Then you can imagine what the frustration could be.
2 hours lost. Sure. For quite a number of people, I suppose.
In this picture that you have, what you have gold coated the electrode. So what? How does gold coating help this?
So what we use in our setup is UV lasers at the shortest wavelength is 243 nanometers. And we did the gold coating to avoid surface charges or things like that from the UV light.
Okay.
Just because the work function of gold is a bit better than that of titanium. So a bit higher, and due to that, it might happen less likely that even if you hit the plates, that you produce charges by that. That was the idea behind, and it works fine. So I don't know whether it actually worked or not. We haven't tried the opposite.
And what is the precision with which these electrode dimensions have to be machined? I mean, these are machined like regular workshop things, right?
They're machined in a regular workshop by a wire erosion technique. I think they have a precision of, I think, around 10 micrometer or something like that in the end. So it's a really, really precise technique for cutting these or machining these blades. Yeah, I think it reduces the surface roughness. Of course, when you gold coat it, there might be again a bit of roughness on the surfaces depending on how good you make that. But yeah, works quite nicely. We have very low heating rates, a few phonons per second only. So I think it was below 5 photons per second or something like that. Of course, that's also due to the fact that the plates are quite far away from the ions. In that case, it's 350 micron or so.
So the distance between the two plates is 350 microns.
I think if the distance that you see is the slit is 0.7 micron or something like that. The distance to the plate might be, of course, you have square root of 2 of the half of that. Or
Okay,
something.
okay.
So it's a little bit more than the 300 micron.
Okay, I think it's good time to start probably, right?
Yes, please go ahead. Thank you. Yeah.
Okay, so it's my pleasure to again welcome back Professor Markus Hennrich from Sweden. And now the floor is yours. So I guess today you would be talking more about Rydbergs, but ions. So let's get started.
Okay, thank you very much, Manas, for the kind introduction. Yes, so yesterday I was talking about ion-photon interaction. Today I want to talk about Rydberg physics, which is currently our main topic of research here in Stockholm. Here in the picture you see a picture from our lab. So it's actually just a picture taken with a normal camera. And in the center you see the strontium ions fluorescing. I think it's a string of something like 12 ions. Yeah, so of course a long exposure on the camera so that they're able to see it. But yes, a camera can see it, of course, with the naked eye you cannot see it. Okay, so talking about Rydberg physics in an ion trap, I want to give a short outline of what I will be presenting. Of course, putting Rydberg atoms, as Tim and Paul already introduced, into the strong electric field of a pole trap leads to quite a lot of new and interesting physics. And what I will start with is the properties of such Rydberg ions that are confined in such a pole trap. I will talk then about also some quantum operations via the Rydberg excitation. And one part is the coherent Rydberg excitation to high-lying Rydberg states. And then the second part will be on a trapped ion entanglement gate via Rydberg interaction. So as I said already yesterday, so we are working with strontium ions, and we want to use them for quantum computation in principle. Of course, in our system, we want to use Rydberg ions then for the Rydberg interaction for also quantum gates. But the qubits are still encoded in low-lying states. So in our experiment, we use the S1/2 ground state of the strontium-88 ions as the 1 qubit state, and the D5 metastable state as the 0 qubit state. So of course there's several Zeeman sublevels here in these two manifolds, and we will use one of these Zeeman sublevels as the qubit state. We can drive the transition between these two qubit states directly by a red laser at 674 nanometers. And typically, of course, you can perform qubit operations in less than a millisecond. So in a few microseconds time, you can do Rabi oscillations there. And the limited lifetime of such a qubit is 0.4 seconds due to the lifetime of the excited state. However, the coherence time in our system is rather on the order of a millisecond. So this is limited by magnetic field fluctuations. Since we're using Zeeman sublevels, these Zeeman sublevels fluctuate in energy depending on the magnetic field fluctuations. If we want to detect the quantum state of this qubit, we shine in a laser at 422 nanometers here, exciting it to the P1/2 excited state. And from there, it decays fast back, scatters a lot of photons. And by fluorescence detection, we can now detect the S1/2 ground state. If the ion fluoresces, it's in the S1/2 ground state. If it is in the D5/2 excited metastable state, then it just doesn't see that laser and doesn't scatter photons. So by distinguishing either the ion being having fluorescence or not, we can distinguish the two qubit states. In principle, if you want to do quantum operations, and I think you will hear quite a lot more about trapped ion quantum operations also with Christian Rose in next week. What you will need to do is you will need to perform gates on these ion qubits. And this, of course, consists of single qubit gates and 2 qubit gates. And with such a set of operations, you can do arbitrary unitary transformations. And as I said before, the laser manipulation of the qubits, these are the single qubit operations. And we will actually use Rydberg interaction for the 2-qubit operations. So the single qubit operations are performed by performing Rabi oscillations by shining in this laser for a certain amount of time. And if you start, for instance, in the S state, you initialize your ion in the S state, and you send this laser pulse for a certain amount of time. It will start Rabi oscillations to the excited state here. And if you then switch off your laser at the right position of time, you will actually make a rotation on your Bloch sphere. And depending on when you stop, you will generate superposition states of this qubit. If you usually with trapped ions, if you want to do entanglement operations, 2-qubit operations, people use most of the groups use the motion of the ions to mediate ion-ion interactions. So what is done there is that one of the laser, for instance, kicks the ions, brings the ion string into motion, depending on the initial quantum state, and then the whole ion string actually knows about the quantum state of this ion because it is now shared in the common motion of the ion string. So you can do conditional operations on a second ion, and by that do entanglement operations. Of course, there's also more sophisticated gates than this that probably Christian will talk next week then about. The state of the art in trapped ions at the moment is that you can do at least 20 qubit full quantum control, probably even more right now. 24 ion entanglement has been shown recently. It's published by a preprint from Innsbruck. Then 53 ion quantum simulations have been performed by JQI in Maryland and in Chris Monroe's group. And all gate errors, so single qubit operations and 2-qubit operations, are demonstrated below an error of 10 to the minus 3. So Oxford has done their really, and NIST in Boulder have done really high fidelity gates and have demonstrated this smaller than 10 to the minus 3 in errors. The entanglement gates, however, are usually rather slow. Typical ion entanglement gates are on the order of 50 microseconds per gate. And this is a little bit slower than for other quantum computation systems, like superconducting qubits or quantum dots. And of course, we would like to speed it up. Oxford has demonstrated some motional entanglement gates that are on the order of a microsecond, and also if it's a little bit above 1 microsecond, have really high fidelity. But what we want to do now is actually we want to combine it with Rydberg interaction and see how fast we can make these gates. So from Rydberg atoms, you probably have heard already a bit how this dipolar Rydberg interaction works from Tim and Paul's presentation. And I think Vlad and Willitsch next week will also talk a bit more about entanglement operations in individual trapped atoms. So what they can do, they can perform also sub-microsecond can perform sub-microsecond entanglement gates via the Rydberg interaction. They have 2D and 3D atomic arrays, which they can couple the individual atoms next to each other. And they can perform quantum simulations with up to 200 atoms. So this was a recent experiment by Antoine Pouet and Orsay. And also they have demonstrated a generation of 20 atom GHZ states. So that's also very comparable to the trapped ion system. They can perform parallel gates in such an atom array, which is a little bit of an advantage compared to trapped ions. On the other hand side, in trapped ions, you can actually perform quantum operations between any ions in a longer string. So it's an all-to-all connectivity. That's the advantage of the trapped ion system. So what we want to do now is we want to combine these two systems. So we want to combine the trapped ions, and we want to use Rydberg interaction for entanglement operations. So this is the main idea that was proposed by Peter Zoller's group in 2008. Markus Müller and Igor Lesanovsky are still looking into that on the theory side, and Igor Lesanovsky has supported us with quite a lot of theory work in this topic. If you want to know a little bit more and see a little bit of a review article, Arezzo Mokberi from Mainz Group has written there the overview article, and I think it's quite useful to get a little bit more into that topic. Okay, so Rydberg atoms or Rydberg ions share, of course, specific properties, and in particular, if you bring ions, the electron into a high-lying Rydberg state, the wave function becomes really, really large. So the Rydberg atom actually the wave function scales with the principal quantum number n as to the power of 2. So for instance, if you go from the ground state of strontium 5 s1/2 to only a 30 s1/2 state, you actually get a factor of 100 already bigger in diameter, which means in volume it's 100 cubed. So it's a really, really huge Rydberg ion compared to a ground state ion. On the other hand side, also many other properties become very, very different. For instance, the lifetime of Rydberg states scales as n to the power of 3, so it becomes longer lived if you go to a higher Rydberg state. Also, transition dipole moment scale as n to the power of 2. The dipole parseability is n power of 7, and quadrupole parseability is n to the power of 11. So depending on where you are in which Rydberg states, some of these properties become really, really strong and dominant actually in your system. Okay, so what we of course now want to do is we want to put such an ion into a Paul trap, and we know that for trapping an ion in a Paul trap, as Didi Leibfried talked about, we need to have quite strong electric fields. Here, a quadrupole field. It's a schematic here of such a quadrupole field with a Rydberg ion here in the center. Of course, the Rydberg ion has now a quite large wave function. So it's quite big, and also the motion of the ion, of course, when it's confined, is such that at some point also it will regions here where the electric field is present. Okay, so and now the question is, of course, when you look at Rydberg atom experiments, usually all electric fields they try to compensate the electric fields as much as possible, so that the energy levels are not affected. And we actually want to put such an ion now in such a strong electric trapping field. And of course, now the question is, what does it do to such a Rydberg ion? The good thing, of course, is the ion is trapped at the saddle point of this electric field. So here you have the quadrupole, and right in the center where the ion is usually trapped, the electric field is 0. There's only a quadrupole field. So if you go a little bit out, you have an electric field, but a dipole field, but right in the center, you only have a quadrupole electric field and no electric field present. So in that sense, even if there's strong electric fields around, in first order, the Rydberg ion will not see the electric field. Only due to the spread of wave functions, it will see the electric field. Okay, what is a Rydberg ion? How does it compare with all the dimensions that you have there? So usually a ground state ion is very, very small, 200 picometer in diameter. The ion motion is then typically ground state wave packet is on the order of 300 nanometers. So it's already much bigger than the size of a ground state ion. If you go to typical Rydberg states of n equal to 50 or something like that, principal quantum number, then you have a few hundred nanometers of wave function, size of the electron wave function, which is of course much bigger already than the ground state wave packet of the ion motion. So one has to take that into account when looking at the physics of the system. On top of that, of course, the ion distance, typical ion distance between such ion in an ion crystal is on the order of 5 micrometer, which means the Rydberg ions, even if you excite them to high-lying Rydberg states, are still individually separated from each other. So the electron wave function doesn't overlap, for instance. So for a typical principal quantum number that we can achieve, you just cannot achieve a regime where the electron wave function will fly, will circle around more than one ion core. Okay, so you have individual Rydberg ions in your ion trap, and you can individually manipulate them by laser light. If you look at typical ion species that are used for quantum computation in different labs around the world, and if you look how to bring such species into Rydberg states, then you will realize that all of these ions have really, really high, need high energy to bring them to Rydberg states. So you need actually lasers with wavelengths of around 100 nanometer to bring it from a ground state into a Rydberg state, or even smaller than that. Unfortunately, the wavelength for below 200 nanometers is already absorbed by air, and you cannot just put your laser somewhere on an optical table and send this light just across the table and send it into the ion trap. So if you go below 200 nanometers, you will need to look to operate a light source already in vacuum and put everything, all the light beams inside a vacuum to your ion. So this is very complicated. You cannot align things so well anymore. Due to that, you probably want to look for a different scheme. Nevertheless, the first Rydberg excitation in Mainz, the second group that is doing Rydberg ions, they have used laser close to 120, a little bit above 120 nanometers for Rydberg excitation. And they've operated that for some time and did experiments with that. But in the meantime, now they also have a system for actually 2-photon excitation of Rydberg states. And the advantage of that is that you have then wavelengths of above 200 nanometers. You can operate it much more easily. So our system, as I said, we are using strontium, and here you see this electron, the energy levels of the strontium that we are using. So as I said, we have the 5 S1/2 ground state as qubit state 1, the 4 D5 halves metastable state as qubit state 0, and we use now, excite now the ions from this qubit state 0, from the metastable state, by a 2-photon excitation into Rydberg states. So we go via the 6p3 halves intermediate state, excited first with a 243 nanometer laser, to this intermediate state, and from there we continue to a Rydberg state by a tunable laser that is tunable between 304 and 309 nanometers. In principle, from the 6p3 halves level with this laser we can drive transitions to NS or ND levels. So these are the two energy levels of Rydberg states that we can directly access with this laser system. Interestingly, both of these states, the Rydberg state as well as the intermediate state, decay mostly back to the ground state with a 95% probability. Of course, it's not a direct decay to the ground state, but it's actually a multi-photon process going down. But the probability to go to ground state is 95%, so almost nothing goes back to the intermediate to the metastable state here. Okay, the experimental setup is sketched here. So we have an ion trap. This is the pole trap that I showed you in the initial picture. Here are the strontium ions in the center. And we have now all the usual lasers for qubit manipulation, cooling and repumping and so on from the side. And we have on top of that 2 Rydberg excitation going along the trap axis. So they actually excite all of the ions at the same time. We have them counter-propagating so that you get 2 momentum kicks in opposite directions, which then means that you almost don't have any Doppler effect in the Rydberg excitations of these 2-photon process, which then actually reduces Doppler broadening in the excitation process, and due to that you get narrower lines. Okay, so this is really, really important that you send these 2 lasers from opposite sides. In the end, we detect the quantum state by a photomultiplier tube, or what is not shown actually here in front, you have also a camera where you can then detect the quantum state of individual ions. The laser system that we're using is, as I said, the first step is a 243 nanometer laser. This is a commercial system that starts with 970 nanometers and then is twice frequency doubled intracavity. To reach something like on the order of 30 milliwatts or 243 nanometers. So it's a diode laser twice frequency doubled. The other system is a self-made laser for 305 to 310 tunable. There we actually do some frequency generation of two lasers, two commercial lasers here, one at 1000 to 1025 and 1550, the other at 1550. We do the some frequency generation of that to 610 to 620 nanometers, and then in the end another doubling stage, also commercial, to 305 to 309 nanometers. So we get there on the order of 75 milliwatts of power in the end. So if you have these two lasers, what you can then do, you can prepare the ion in this 0 qubit state, the initial state 45 halves, and then you can excite the ion into the Rydberg state by this two-photon process. From there it will decay mostly back to the ground state, and if you then do fluorescence detection, what will happen is that if you have excited to Rydberg state, you will see the population transfer from the 0 state to the 1 state. The ion will fluoresce. While if you haven't excited to Rydberg state, for instance, because your laser was detuned, it will just stay in the initial state and will stay dark. So depending on the fluorescence appearing or not appearing, you know whether you excited to Rydberg state or not. If you do now spectroscopy of such a population transfer by doing the spectroscopy, you can see actually a Siemens structure of population appearing. So starting from the, actually in this case, the 4D3 half state, we just, in principle, sorry for that, you can also start from 4D3 halves, go via 6P1 halves to NS states. If you do that, what you can then see is the spectroscopy of individual Siemens levels. And since you start in an equal superposition of all individual Siemens levels, you actually have 4 different possibilities to go to Rydberg states, and you can see the Siemens splitting in these levels, and it's consistent with the magnetic field of 2.9 Gauss that we have in our system. If you select specific polarization of your laser only, then you can only drive one of these transitions, and you only see one resonance. If you go instead to Rydberg D states, then the thing gets a little bit more complicated. And the reason for that is the D states actually couple to the quadrupole field. So the reason for that is that the D states have a quadrupole moment. And since they have a quadrupole moment, the quadrupole moment actually interacts directly with the quadrupole field. So S1 halves and P1 half states are not affected because they don't have a quadrupole moment. But everything with J bigger than 1 halves has a quadrupole moment, and due to that interacts with the quadrupole field. The theory behind that is that you have a trapping potential that is confining your ion inside the ion trap, which consists of the oscillating term. So this is an oscillating term that is applied to the blade electrodes in our system, that generates the quadrupole here in X and Y direction. It's a radio frequency field, and the gradient of this radio frequency field is really very high. So alpha is actually very big, while a static field where you apply electric field on the end cap electrodes, that's relatively low, the gradient here. So this is a smaller component compared to the radio frequency field. So alpha is big, beta is rather small. The difference between here is actually 2 orders of magnitude. Okay, so
Markus, may I disturb you now? There are a couple of questions. Do you want to answer them now, or?
I think let's make a break and answer them now. Yes.
Okay, so I think there are 2 questions from Mahi, which says, I guess it's about the coherence time of the Rabi flops that you showed before on strontium.
Yes.
How many cycles you observed here in a single qubit beautiful Rabi oscillation?
Okay, the Rabi oscillations, actually this picture that I showed you there might be still from a calcium ion. I'm not 100% sure. Our coherence time is, as I said, on the order of milliseconds, so we probably get something like 20 Rabi oscillations before we see the decoherence. It's not super good, okay? But so we have we have, as I said, on the order of milliseconds of
Right.
coherence time.
In the second question from him is, do BBO crystal cause frequency or intensity fluctuations trouble?
The BBO that we use here is of course you have, well, sorry. Here in the 243 nanometer laser, the BBO has a walk-off in the crystal. And the problem that we have there to some extent is due to the walk-off that it's not perfectly single mode. It's a little bit off, so not really, the m² parameter is not perfect. So it's a little bit more difficult to couple that into a fiber. We have special fibers, UV fibers for that we manufactured ourselves. And the coupling efficiency is not super good. That's the main problem that we see there. Of course, on top of that, since it's 243 nanometers, actually the power is not super stable, so it will drop over the course of a day by something like 50% or so. Okay, so you optimize in the morning, and then in the evening the power is only half. But we are currently getting an upgrade from the company, and we hope that it's getting better then.
Okay. I think there is one more question, two actually. One is more a confirmation that the use of two-photon scheme is because of operating in the atmospheric pressure. This is more a confirmation if it is true or not. That instead of 100 nanometer, using 200 nanometers or 300 nanometers to.
It's just the laser system become much less complicated. The 120, I think 6 nanometers that MINE's used, this is a whole lab to just generate this light. And it's very, very sensitive to all alignment. And
I guess MINE's already had one. That's why they
yes, exactly. They already had one for actually a hydrogen alpha experiment.
Exactly.
And,
okay,
due to that, you don't want to build it yourself.
Then there is a question about if the two photons are considered co-propagating in the two-photon excitation scheme, how much broadening will be caused due to the wave vector mismatch?
So there's a little bit of a wave vector mismatch. You can calculate the effective wavelength of the two-photon transition is something like 1200 nanometers or so, which means by the localization of our ions, we are well in the Lambdicke regime. And due to that, you actually can resolve rather sidebands than see a Doppler effect. So it's not really Doppler broadening anymore. Only if you the position changes more than the wavelengths, you actually see the Doppler broadening.
Perfect. I think there are no more questions. Maybe we can just go ahead. Yeah.
Perfect. Yeah.
Thanks. Yeah.
Great. Okay. So coming back to the coupling of the D states to the quadrupole field, I said you couple the D states, since they have a quadrupole moment, couple mostly to this oscillating part of your trapping potential. You can calculate the coupling by, it's easiest if you look at actually you transform this formula by spherical harmonics. And then you actually see that there's a term here from the DC term that only leads to DC static shifts, while the AC term actually leads to the coupling between different Zeeman levels. So there's a delta M equal to ±2 involved in there. Okay. So the RF field actually couples now, for instance, in the D3 halves manifold, couples now the -3 halves level with the +1 halves levels, because there's a delta M equal to 2, and a -1 halves level to +3 halves. If you then look at the spectra, and we measure the spectra here only for a relatively low principal quantum number n equal to 24, you see that in the spectra, you see many, many lines, and this is due to this coupling with the quadrupole field. Reason for that is that the coupling actually oscillates in time due to this cosine omega t, and this gives you Floquet sidebands. And you have to actually calculate Floquet levels in this oscillating quadrupole field. And if you do that, and if you simulate a spectrum, then you see that the spectrum actually doesn't match the theory without quadrupole interaction, but you actually have to take this quadrupole interaction into account to actually match where all of these lines are. So yes, you see the interaction of these d levels with the quadrupole field, and if you go to higher principal quantum numbers, of course, this will get much worse. So you probably don't want to go to an n equal to 60 d level, because there you just need CF4 sort of lines and nothing else. Okay, so let's stay at the S1 halves and P1 halves levels where you don't have a quadrupole moment, and do some physics with that. So the initial experiment that we've then done, we started in this 4d5 halves initial state. We excited first just to the intermediate state with the first 243 nanometer laser and looked at the spectrum here. So without any coupling laser, without a second laser here, we just see the resonance line of this transition. If we now switch on the upper second laser, what we see is, if we make that very, very strong, is we see that we get trace states between these two levels. So the trace states, of course, we can probe now with a weak 243 nanometer laser down here. And you see an outer tone splitting appearing. So, which means you see two lines here, which are these two trace states, and they follow here symmetrically around it. So we are perfectly on resonance with the upper level, and by the splitting here, you can directly measure actually the Rabi frequency of your coupling laser. Okay, once you see such a such a outer tone splitting, you can try to actually do a little bit more with that. So what we then did is we controlled the Rabi frequency of these two lasers. And if you look at the three-level system, the initial state, the intermediate state, and the final state, zero, excited state, and the Rydberg level, then they are coupled, and the lower laser couples the first two levels, and the upper laser couples the upper two levels. So this is the Hamiltonian. There's no detuning, so this is here 0, so you're really on resonance to that. If you then calculate eigenstates, similar to what I've explained yesterday, you get one dark eigenstate. The dark eigenstate, dark in parentheses, is we call it dark because it doesn't contain the intermediate level. Okay, so it's a superposition only of the initial state and the Rydberg level, which lives for a relatively long time. The relative amplitude of these dark states can be controlled by controlling the Rabi frequency of this probe and the coupling laser. So, for instance, if the probe laser is off at the beginning and the coupling laser is on, then the initial state will be equal to the dark state. So the Rabi frequency omega p will be 0 and only omega c will be on. So 0 is equal to phi dark. If you now switch on omega p, the probe laser slowly while switching off omega c, then you get an arbitrary adiabatic following of this of the system in the dark state, and you adiabatically transfer population from this initial state 0 to the Rydberg state. This is a stimulated Raman, of course not really Raman, a 2-photon adiabatic passage. Okay, if we then map the population up by such a such a pulse sequence here, we excite it into Rydberg state, and then of course from the Rydberg state it will decay to the other state, and we see the population transfer, which means if we do such a pulse, we almost don't have any population left in the initial state. We can detect that, and this is the yellow point here. If you want to know, was it really excited to Rydberg state? Because in principle, also the intermediate state decays to the other level. In principle, if we had population just brought up into the intermediate state, we would see the same thing. So what we need to prove is we were already in the Rydberg state. And for that to do, we do 2 stirrup pulse sequence, one going up, and then reverse the sequence to go down again after some time. And by doing that, we go first from the initial state to Rydberg state by this adiabatic transfer. We wait for some time there, and then we return the population back to the ground state. Of course, everything that has spontaneous decay in between, we will not be able to return. But we see here that we can return 60% of the population back to the ground state, even after something like almost a microsecond. So quite a lot of population actually ended up in the read-back state. If we change the waiting time here, we can actually measure the lifetime of our read-back state. And here what we then see is a lifetime of something like 2.3 microseconds, which is consistent with theory, I would say. The theory is for a 42 S1/2 state, and with including blackbody radiation losses, actually. We can then make a very, very short double stirrup sequence going up and down very fast. And we see actually that we can transfer 83% population back to ground state, which means that the stirrup going up is at least 91% efficient. Actually, there was some theory paper from Nikolai Vitanov's group recently who showed that due to interference effects, it could be even higher than 91%. Okay, so we have a quite high efficiency for bringing the population to read-back state. It's a coherent excitation. And at the moment, this is actually limited by the Rabi frequencies that we can generate and the line widths of our laser. And we have improved on that, so we also have improved the efficiency quite significantly. Okay, now looking a little bit more into the physics of read-back ion in such an ion trap. It's getting a little bit more complicated. It's not just the interaction of the D states with the quadrupole field. We have additional effects, and the additional effects, if you go to higher read-back states, come from the fact that your read-back states are highly polarizable. Which means depending on where your ion actually is located in your ion trap, it will see here an oscillating electric field and will be polarized by this oscillating electric field. So meaning if you have such a trapping potential, as the trapping potential that I showed you before, you have the oscillating electric field here, the quadrupole field, and you have the DC quadrupole. And as I said before, alpha is usually much bigger than beta, so you can usually neglect this term now for this effect. So only if the read-back ion now moves radially in such a linear pole trap to the X or Y direction, then this effect actually matters, while if it moves axially, there's almost no change in electric field compared to radial direction, and due to that, you don't see much of this effect. So electric field, of course, is the gradient of this potential. So which means if you put a gradient here, you make a derivative of that either in X or Y direction. So you get a linear dependency on X or the linear dependency on Y of the electric field. So the electric field will grow linearly depending on in which direction you go, theoretically out to the outside. Due to the Stark effect, the Stark effect is minus 1/2 polarizability of your state times electric field squared, the average of that. Which means if you have now a linear dependence of your electric field going up, if you go outside, then this squared will lead to an additional potential that is depending on R squared. So this is proportional to R, and this is proportional to R squared then. If you go, so electric field is proportional to R, electric field squared is then proportional to R squared, of course. Which means you have now, due to this polarizability, you have an additional potential, either a additional potential that is positive or negative depending on the sign of the polarizability. And this is, of course, an additional potential, additional to the confining potential that you usually have. Which means you have in the ground state, you have one type of potential here, for instance, the 45/2 level, where the polarizability is almost 0. This will be one trapping potential. if you go to Rydberg state, where this parasibility is not negligible anymore, you will have this additional potential due to the Stark effect, and this will now modify your trapping potential. So it will just have a slightly different frequency here. Okay. Depending on Rydberg state, of course, the change in frequency can be quite significant. So if you go to 60, 70 or something like that, you might even reach anti-trapping states depending on your parasibility. Okay, so what does it mean now for the spectroscopy? If you have different phonon number states here in a ground state, for instance, if you start in a 0 phonon number state and you go to a 0 phonon number state in the Rydberg state, then you will have one frequency. However, if you go from 1 to 1, you will actually have a little bit of different frequency due to this change in trapping potential, because the differences in energies here is slightly different than the difference in energy down here. Okay, so you will have one frequency going up here, and slightly different shifted frequency going here, and a little bit more shifted frequency there. So the shift is n times h bar delta omega of the change in trapping frequency here. So since these wave functions here are still more or less very, very similar to the wave functions down here, meaning that you almost only have transitions from 0 to 0 and from 1 to 1 and from 2 to 2, because the other levels here are more or less orthogonal to that. Okay, so it's if you multiply this wave function with that, it's almost 0. Okay, so what we will see is different transitions from 0 to 0, from 1 to 1, from 2 to 2. And we can now actually prepare our ion in specific motional states, Fock states, and look at the resonance frequency of our transition. And if we do that, and we prepare different Fock states here, we actually see that depending on the Fock state, your energy, our resonance will actually shift slightly. And by that, you know this how much this frequency of your Rydberg state is different, the trapping frequency, than the ground state. Here, I think in this experiment with 42S, we had on the order of 40 kilohertz per phonon. So this is yeah, what you would expect also from theory, from the parasibility of your Rydberg state. Of course, if you don't start in a Fock state of motion here, but if you are in a thermal state, for instance, just after Doppler cooling, you usually have a population of average population of your phonon states of n equal to 10 or something like that, or 15. Then many states here will be populated. And depending on the initial state, of course, you have a slightly different resonance frequency. So if you have a thermal population, you will get now a distribution of resonance frequency. So it's a broadening of your line that happens due to that. So if you have a sideband cooled ion that is most of the population a ground state, you get a narrow line. But if you have a thermal state just after Doppler cooling, then you will see that it's actually a broadened line that is consistent with this broadening to this NSG shift. Okay. Of course, this also affects our Rydberg excitation. If you have a broad line, and depending now on the initial state, you will be slightly detuned with your excitation, which means if you're detuned, of course, Rabi oscillations, you know that the Rabi oscillations actually get faster or slower depending on the detuning. On resonance, they are slowest. And this will actually wash out Rabi oscillations in your experiment. So depending on the line width of your resonance, you will also get an effective decoherence of your Rabi oscillations. So here is the experiment. You see Rabi oscillations of the 2-photon excitation to Rydberg states from the ground state, if it's ground state cooled with a sideband cooling, or if it's just Doppler cooled. And you see that in a Doppler cooled ion, there's no Rabi oscillations visible anymore. So you will need to go to sideband cooled ions to actually do these Rabi oscillations properly. Okay, but we can play an additional trick to circumvent that to some extent. So If you drive a transition between Rydberg levels by a microwave field, then you can drive transitions, for instance, from the NS1/2 to an NP1/2 level. So the microwave field now couples these two levels. And for instance, for any principal quantum number n equal to 46, you couple these two levels with a microwave frequency of around 120 gigahertz, which is quite a high frequency, of course. You need a special synthesizer with multiplier and so on to generate that. But it's also a commercial system that you can just use and shine similar to a laser just to your vacuum window into your ion trap. By that, you can couple then these two levels. And since NS states and NP states have opposite sign in the polarizability, you couple now one state that has a positive polarizability with another state that has a negative polarizability. And if you couple these two levels with a microwave field, you can actually generate dress states of these two levels. And by that, actually tune the polarizability of your dressed level. Okay, depending on whether it's positive or negative, the polarizability of your, so the combined state has the average of the two polarizabilities in the end, depending on the relative populations of these two levels. We looked now into that, also again looking at the different resonance transition frequencies for Rydberg excitation, depending on whether we are only going to S state for the 6 S's, for instance, here just this green light, depending on the initial phonon numbers. And you see again, like before, this shift in energy depending on the phonon number, so depending on where you go up here in transition. If you go to an equal population of S and P states, so a dress state that is resonant, you put your microwave on resonance and you couple them quite strongly, then you have an equal population of these two levels. And since the P level actually has a higher polarizability but with opposite sign, then the S levels, you actually see the shift going in the other direction, which means instead of having a weaker trap, you actually have a tighter trap in the Rydberg state. Of course, if you now tune the relative amplitudes of these levels in a right way, you can actually tune your effective polarizability of the stress state in such a way that it's equivalent to the polarizability of the ground state, which means now the stressed Rydberg level has the same trapping potential as the ground state, and which means due to that, you don't get an energy shift depending on your initial state anymore. Nice thing then is you can look at Rabi oscillations, and the Rabi oscillations that you usually observe in a ground state cooled ion here. You can also get the same now in a Doppler cooled ion only with an average population of n equal to 10 or 15. Here, the Rabi frequency is slightly lower, but this is actually expected because in the Rydberg excitation, we only couple to the S component of this state. And due to that, the Rabi frequency is slightly smaller. So we still see the Rabi oscillations appearing even for a Doppler cooled ion. Okay, more trap effects. So still not everything is completely simple. I think you have heard about micromotion already also today by Stefan Willitsch, the micromotion that is inducing in the collision between hybrid systems between cold atom gas and trapped ion. Also here we see micromotion effects. So micromotion means what you do is you apply an additional electric field to your trap, and this shifts the trapping potential that you usually have. So usually the ion is trapped here in the center. If you have now an additional offset electric field, the equilibrium position is shifted a little bit to the side. This basically equivalent. You have a force that is actually in such a trapping potential is a tilt of your potential here that is added to the normal the quadratic potential, and this shifts your potential and shifts it a little bit also in energy. Okay. Of course, the shift, how much it is shifted, and by how much it also goes down. This depends on the on how much your trapping potential is confined. Okay, but on top of that, also since you now have an oscillating electric field at your equilibrium position, you get an additional Stark shift for a polarizable Rydberg state. So you have at the equilibrium position an oscillating electric field. This oscillating electric field shifts your energy level. And if you now measure the resonance frequency of your Rydberg excitation, then due to this polarizability, the Stark effect actually leads, depending on what micromotion voltage you apply, will actually shift your energy level on top of that. Okay. Yes, so this is actually a micromotion effect of your Rydberg ion, which shifts the energy levels. On top of that, as I said, this offset electric field will apply a force on your trapping potential. The force will, depending on how strongly the ion is confined, will either shift it by some amount or a little bit more, a little bit less. So depending on how much it is fixed at this position, a certain force will shift it more or it will shift it less. And since the ground state potential is different than a Rydberg state potential, the shift will be slightly different if you now apply such a force. Which means if you're not perfectly micromotion compensated, the ground state potential and Rydberg state potential will be slightly shifted with respect to each other. And if you now drive transitions, you will see now that this wave packet and this wave packet are not perfectly the same anymore, or this one is not perfectly orthogonal anymore. Okay, so you can actually drive transitions now between this wave packet and that wave packet because they are not orthogonal to each other anymore. Which means if you're now shifting these two potentials with respect to each other, what you will see is that you see a resonance line, but you also see from 0 the resonance line going from 0 to 1 and from 0 to 2. Okay, so these are now sidebands in your spectra that you will see appearing if you're not perfectly micromotion compensated. This is of course expected, and depending on how much the overlap, the two potentials overlap, you can actually calculate how much these sidebands you will see. And of course, it also depends very much on the relative stiffness of these two trapping potentials and by how much they are shifted, how much force you apply. So depending on that, you can drive sidebands either in one direction or the other direction. Okay, maybe, so this is all what I wanted to say about trapping effects at the moment. If there's any questions now, maybe we could make a short break before then going really to the quantum operation, quantum gates.
Right, there are two that's on the chat. One is, does it matter if the lasers are edge emitters versus surface emitters because we have fiber coupling? I guess this is related to the Rydberg excitation, but not sure what it means.
So in principle, I don't 100% understand what is edge emitters is meant. Yes, we do have fiber coupling. I think probably it's related to the mode that is generated then from the laser. Since we have always single mode fibers, the mode actually filters out everything that is not contained in all the other modes that are not going into the fiber. And then after the fiber, you will have a single mode independent of what type of laser you actually have sent in that. Of course, if you lose a lot of power because it has not a small overlap with the single mode of the fiber, that is something that you don't want because you want a higher Rabi frequency. Of course, you want to have their lasers as much single mode as possible. So,
yeah, I think that was the question. The second one is about, in experiment, what time do you send the microwave after 2 photon excitation or together with the laser from the beginning?
We have the microwave always on. Actually, we don't switch the microwave so far. We have the capability to do that, but we haven't used it yet. So the microwave is always on, which means we always have the dressed levels of the Rydberg coupled system. So it's always a superposition of SNP at the moment.
Okay, there is one more. Can this experiment be performed for higher principal quantum number Rydberg states, such that the RF frequency coupling to the nearby P state can be smaller? I guess
so
yeah.
Maybe one answer. We can go. I think our record at the moment was n equal to 56 or something like that. But in principle, one can go to slightly higher Rydberg states than that. But at some point, the trapping field will actually also ionize the Rydberg levels. Reason for that is that if you have the wave function, and if the wave function is so big that the electric field becomes too big, at some point you actually have your confining for the electron, the confining potential of the core so much tilted to the side that you will get tunneling of the electron to the outside, or even just that you have not trapped states anymore for your electron. So at some point, if you go to too high electric fields, you will lose the electron actually.
Yeah, I think that's all for the time being. Yeah.
Mm-hmm. Okay, perfect. Then, okay, so once we have now understood all the trap effects, the trap effects, as I said, what we actually want to avoid is at the moment for these experiments is any micromotion. So we do perfect micromotion compensation, or as perfect as much as we can do it. And then on top of that, we go to the NS states and we apply the microwave field to avoid any effects of the motion by going to the zero possibility Rydberg states, or at least for some of the experiments that I will show. On top of that, we can do ground state cooling as much as possible so that in our system, the motional effects also become minimal. So in the first experiment that I show you, we actually did ground state cooling and no zero possibility tuning, while in the second experiment that I will show you, we also did the zero possibility tuning. I will come to that back later. So if you want to have a strong dipole-dipole interaction between Rydberg ions, then we have to think what can we actually do to get such a strong dipole-dipole interaction. Unfortunately, the usual van der Waals interaction that many people use or most people use in Rydberg atoms scales as the core charge to the power of -6. Core charge means the remaining core if we take the Rydberg electron out. Okay, so in our case, since we have an ion, we have a doubly charged core and a single Rydberg electron. Which means Z in our case would be equal to 2. But compared to Rydberg atoms, where Z is equal to 1, this of course is already a factor 2 to the -6 that reduces the strength of the van der Waals interaction. Okay, so it's a relatively big factor that happens there. The reason for that is just, yeah, we are using ions. And if you go to the same principal quantum number, of course, since the core is more highly charged, the electron will just be closer to the core. Okay, the Coulomb attraction is much bigger. Okay, there's already in the initial proposal of using Rydberg ions, there was a solution, the microwave dressing. And the microwave dressing actually couples an S and a P state, and these S and P state are, as I said, they're dress states of S and P, And the dress states of SNP actually have oscillating dipole moments. I will come back to that in a second and explain it a little bit more intuitively. As I said, we use here in this experiment a 46 S1/2 to 46 P1/2 transition with a microwave frequency of 120 gigahertz. Okay, going a little bit more into how big is the Rydberg interaction for different schemes. The van der Waals interaction for our system would be on the order of 2 pi times 20 kilohertz. If you compare that to a few microseconds lifetime of the Rydberg states, then you see that within the lifetime of our Rydberg states, it's just not enough time to get a full energy excitation of one quantum of energy between these two ions. So 20 kilohertz is much slower than the few microseconds that you have as a lifetime. Okay, so the dipole induced by this external microwave field, there we get a direct dipole-dipole interaction, and the interaction strength scales as set to a power of -2, and also it scales as the distance to the power of -3. So it's a dipole-dipole interaction. It's not a second-order effect, not R to -6. And the strength here that we expect is on the order of a few megahertz, depending on the distance. This year, the 2 pi times 2 megahertz is for a distance of, I think, 4.5 micrometer approximately. So it's a typical ion distance between two ions. So how does it work if you have these Rydberg levels and you couple them with a microwave field? Then an s orbital and a p orbital, of course, have a different type of symmetry. And now if you drive a transition between the two of them, you couple these two levels and you can go into a rotating frame of the coupled system. And in a rotating frame, you have now, actually in a rotating frame, you will have just s plus p or s minus p or something like that. But in a non-rotating frame, you have an s plus e to the I omega t, which is the omega of the microwave frequency, plus p. And depending on the time, now you will get either a plus sum of the two wave packets or a plus minus, because this changes its phase with time. Okay. So depending on the time that you look at it, the sum of this superposition will be now an electron that either has more population above or more population below the core. So together with the core and the electron being above or below, you will actually get such an electron wave function that oscillates around the core, and due to that you get an oscillating dipole. Okay, so this is how the setup looks like. Here our microwave source that generates the 120 gigahertz. We have here just two gold mirrors that reflect this microwave that is coming here from the microwave horn, reflected into the ion trap here at the side, just through the normal window. And then we do spectroscopy with that on our ions. There's a few tricks that we have to do. For instance, here you see, actually, maybe in that setup not yet, but we actually have to ground our mirrors so that we don't get so much grounding effects. Of course, it's a microwave, and microwave is already sensitive to also how everything is grounded around. Okay. So what we then do is we have the same scheme as before. We have our qubit here in the 1 is our 5s1/2 ground state, 0 is our 5d5/2 metastable state, and we do this two-photon excitation in the Rydberg state, and the Rydberg state is now such a microwave dressed Rydberg state. So we couple an S state with a P state, and here, due to the quantization axis, the B field is along the trap axis, and the microwave field is perpendicular to that. We drive sigma transitions between between these individual Zeeman levels. We then couple these two levels here, and we excite to these Rydberg levels. So two of these ions next to each other, of course, see the same microwave field, the wavelength of the microwave is very, very big. So there's basically the same phase and the same amplitude of the microwave field on both ions. Which means due to that, they will actually also oscillate in phase to each other. So the microwave, the oscillating dipole will be an oscillating dipole where both of these ions oscillate in phase. Which is of course important if you want to look at the interaction strength. If you then do spectroscopy of these dressed levels, microwave coupled levels here, you can change the microwave detuning, and you can change the detuning of your two-photon transition to the Rydberg state. You can look where your resonance is, and depending on the tuning of the microwave field, if you're on resonance with the transition here, you will of course see that you have an equal splitting of the plus and the minus state, which are the two dressed levels of S plus P and S minus P. Of course, if you're detuned, then you rather can only excite the S level, because that's where your two-photon excitation goes to. And then only the S level will be excited here by this two-photon transition. If you're exciting into the equally coupled levels, of course, you only also couple to the S level here with your two-photon transition. But since the dressed level also has half P component, you can also excite that. Okay, what do we want to do? Of course, in principle, for neutral atoms, we use people use the Rydberg blockade for quantum gates. The main idea for that Rydberg blockade is that if you have a Rydberg-Rydberg interaction and you have two ions or atoms next to each other and you excite them with the same laser, then if one of the atoms or ions gets excited to Rydberg state, then once you end up in a state where one of these two atoms or ions will be excited, and from there you would now need to excite a second atom or ion. And due to an interaction, of course, the interaction shifts the energy level. It's interaction, of course, it just diagonalizing Hamiltonian leads to an energy shift, and due to that, the same laser is not anymore resonant to this transition. Which means due to interaction, the interaction shifts this transition out of resonance, and this laser will not be able to excite the atom or ion anymore. So what you only will see is one of the atoms or ion will be excited, but the second one will not be excited anymore. So it's a Rydberg blockade of this excitation. We now investigated that in our system by starting now again in the DD state, two ions next to each other. And we first did not do any microwave dressing, which means if there's no microwave dressing, there's no oscillating dipole, so there's no dipole-dipole interaction. Of course, there's still van der Waals interaction, but this one is very, very small. And if we do the experiment there, we do Rabi oscillations starting from the initial state and excite both of the ions next to each other. We can compare the signal that we get, either one ion being excited to Rydberg state or both ions being excited to Rydberg state, to the case where we only have one ion and we only excite one ion to Rydberg state. So the green curve here is only one ion, Rabi oscillations of one ion, while the red and the blue curve are now two ions next to each other and both of them excited to Rydberg state. What happens then is that the green curve has a certain probability after a certain pulse sequence, pulse length to being excited into Rydberg state. For instance, here it's 0.8 something. And if you now have two ions next to each other and they are independently excited, then you have the P, the probability here of one ion being excited, just squared. Okay, so each of them gets independently excited. P and P squared should be the case for two ions. So P squared should be the case for two ions with respect to one ion. And we see that the red curve is actually following quite well this P squared curve of the single ion excitation. The blue curve is, of course, P times 1 minus P times 2. So it's also just the independent excitation of the two ions. And, well, data here deviates a little bit, but in principle, it follows more or less what we would expect. On the other hand side, if you now apply your microwave field and you excite to the stressed Rydberg levels, you will expect that the two oscillating dipoles interact with each other. You have a Rydberg-Rydberg interaction, and due to that, you cannot excite both ions at the same time into Rydberg state. And what you see here in the data is, as what we would expect, the green curve of a single ion being excited to Rydberg state, a Rabi oscillation, follows the same curve as before, but the red curve now is very, very strongly suppressed, which means it's not anymore possible to excite both of the ions at the same time into Rydberg state. So we see actually this shift out of resonance of the two ions being excited into Rydberg state, and due to that, the Doppler, the Rydberg blockade is proven by that. On top of that, we see here that the blue curve is just the same as the green curve, but a little bit faster. A square root of 2 faster actually as the green curve. And this is actually expected because we couple with this laser actually this equal superposition of RD minus DR of one ion being excited to Rydberg state, while RD minus DR is not coupled at all. It's due to the coupling of one versus the other that you expect a square root of 2 speed up of the Rabi frequency. It has been, of course, also observed with neutral atoms for quite some time ago. I think in 2007 or something like that, in the groups of Max Huffman and Antoine Prouet. Okay, so to summarize this, we have observed the Rydberg blockade. The interaction is strong enough to shift the Rydberg state out of resonance to this exciting laser. The simulation that you actually see here is the simulation simulating that with on the order of 2 megahertz interaction strength, as we would expect from the distance and from the dipole moments that we have. Okay, next step is of course to make a gate out of that. And for making a gate out of such an interaction, we go to a slightly different scheme. We don't anymore use a Rydberg blockade, but we actually go back to our coherent excitation via stirrup and use the interaction for an energy shift that delivers a phase. This is a so-called interaction gate. I will explain a little bit more in a minute what such an interaction gate means, but you have to keep in mind that we really put both of the ions into Rydberg state next to each other. So we apply a stirrup sequence. So as we had it before, we have the Rydberg laser 1, Rydberg laser 2. We apply the population transfer from the initial state to Rydberg state by this switching on and off. So having first the upper laser on and the lower laser off, and then switching on the lower laser and switching off the upper laser. Okay. Then the population is transferred from the initial state to Rydberg state, and if we reverse the process, it will be transferred back to the zero state. Here you see a simulation of that with Q-tip actually. So if you start with both ions in a zero state, you will excite them both into Rydberg state, at least with some probability, and then return to initial state. If there's only one ion, that's the dashed line compared to that. The whole time here is on the order of 700 nanoseconds, so it's quite fast. It's sub-microsecond for operating such a gate. So it's a really fast gate for trapped ions. So what does it mean, this interaction gate? So I said you have an Rydberg-Rydberg interaction, and if we now start in a 0-0 state, so this is initial state that is excited to Rydberg state, we will excite both of the ions into Rydberg state, and due to interaction, we actually have an energy shift. This is usually causing the Rydberg blockade, but here it's actually just causing an energy shift of this level. And then after returning to initial state, this energy shift over time will actually lead to an effective phase shift, which leads to an effective phase shift of -1. On the other hand side, if only one of the ions is in state 0, then only one of the ions is excited to Rydberg state, while the other ion stays in state 1. And since there's no Rydberg-Rydberg interaction, there's no energy shift and there's no phase. Also, if both of the ions are in the S1/2 ground state, none of the ion is excited to Rydberg state, no shift, and we stay just in state 1,1. So the Rydberg interaction induces a phase, and this phase can be controlled in such a way, interaction strength times time, that it's in the Rydberg state, that we get exactly this pi, this -1 state, this pi phase. This is a so-called controlled phase gate, if we operate it like that, and it's similar to a C0, one of an entanglement operation gates. Okay, so we apply such a gate on equal superposition of 0 of 1 and 1 for both of the ions. So we start in 0 plus 1 times 0 plus 1. And if we then apply this gate, the 0, 0 will actually get a -1. Okay, and if you then use this 0 plus 1, 0 plus 1 with 1 minus and 0, 0, you will end up in such a state. So for one of the ions in the 0 state, you will end up in a 0 minus 1 state. Well, for the first ion in state 1 state, you will end up in 0 plus 1 state. So effectively, this is the phase that is induced to this conditional phase gate. So depending on the state of the first ion, you have a conditional phase on the second ion. And this we can detect by detecting the phase by Ramsey analysis sequence. Depending on the state of the first ion, we have either one phase or the other phase on the second ion. We can also analyze the fidelity of this maximally entangled state that we generate. If we start in the equal superposition of 0 plus 1, if it's both ions, we get this maximally entangled state. And we can actually analyze the fidelity of this maximally entangled state by so-called parity oscillations. What it does is similar to a GZ state, you only have populations and coherences, so only in the density matrix, only 4 elements. And by measuring the populations and by measuring the amplitude of these parity oscillations, you can measure the off-diagonal elements of this density matrix. Okay, so it's you measure with a population, you measure diagonal elements of the density matrix. With the parity oscillations, you measure the off-diagonal elements of the density matrix. With that, you can characterize the fidelity of your state. So from parity oscillations, then you can characterize the fidelity of this maximally entangled state with this kind of a rotated belt state. And what we get as a fidelity of that rotated belt state is something like 78%. So it's of course not a gate operation that is at 10 to the minus 3 level. And certainly we have to work on getting this fidelity significantly higher to use it for something. Nice thing is, of course, it's only 700 nanoseconds. And in principle, we think we can even speed up this system quite a lot by putting the ions closer together and bring it to higher Rydberg states. So here a little bit of an error budget of this gate operation. The Rydberg state lifetime at the moment, since it's still 700 nanoseconds, gives an error of something like 3.5%. But by going to higher Rydberg states, we get a longer lifetime of the Rydberg levels, and at the same time a higher interaction strength, which makes it faster. Okay, so by going to higher Rydberg states, bringing the ions closer together, we think that we can suppress this to significantly below 1%. This Rydberg state lifetime error. On the other hand side, there's quite a lot of technical errors, laser line width, and non-adiabaticity of syrup, microwave power fluctuations. These can be avoided by making the lasers better and by actually increasing the power of the Rydberg excitation. So going to higher Rabi frequency, which can actually be done by just focusing our lasers better. By that, we can get higher Rabi frequency, and due to that, suppress this non-adiabaticity quite a lot. Also, microwave power fluctuations, actually we have these dressed Rydberg levels, and they are split by the effective Rabi frequency of our microwave. And which means if the microwave power now fluctuates, these energy levels will fluctuate in energy. And this is effectively increasing the coherence of our excitation. And we certainly need to also get some additional power stabilization for a microwave. The coupling to the motion, interesting, is not so bad. Coupling to motion here is the effect due to the interaction. Of course, you also have forces on the ions. So due to the action, you have a interaction potential. I showed you the Coulomb the Rydberg blockade. Depending on the distance, the interaction goes up, and due to that, you get an effective force on the ions. And the calculated error here is actually how much the motion of the ions gets entangled to this Rydberg states, to the quantum states of the ion by these forces. And this is actually relatively small and also doesn't scale so bad with the number of ions. How does it compare to other gates in trapped ions? Here is a graph of many different gates that have been realized. Here you see actually the gates by the NIST and the Oxford groups on really high fidelity, below 10 to the minus 3. But you also see here gates by the Oxford group from 2018, where they show close to a microsecond operation. All of these gates here are laser-based gates via the motion, while the red point here is our Rydberg interaction gate. So we are not the fastest. Oxford group is still a little bit faster than us. But I think our gate is not limited at that point, while the motional gate actually gets quite more complicated if you want to make it faster than the oscillation period of your ion motion. And that's actually the regime where you would need to operate that. So we can bring the ions closer together, go to higher Rydberg state, and then go to a regime down here, limited by the lifetime of our Rydberg coherence of our Rydberg lifetimes. Make it faster and lower error. Interestingly, the gate also doesn't slow down in longer ion crystals. Usually for motional gates, you need to have to control all the different modes of your ion crystal, and it gets more and more complicated to operate fast gates if you put more ions in the crystal. For us, we can actually operate such a Rydberg interaction gate between any two neighboring ions in such an ion string. And since the distance between these ions in an ion string actually gets smaller and smaller, the more ions you put inside, because they're compressed by the outer ions, pushing the inner ions together by Coulomb forces, it actually results that the ions, the interaction gets faster. And the gate gets faster the more ions you put into the trap. And we actually did an initial test on this. Of course, in that case, we were still limited by our Rabi frequency of our Rydberg excitation lasers, using the gate in a 12 ion string. So we actually did an entanglement operation in the two central ions in a 12 ion string. And also here, it has actually the same gate time, 700 nanoseconds operation time. We used in this case the zero parsability states and a similar ion distance. The gate fidelity that we can measure here is on the order of 63%. We know where the higher infidelity comes from. It's due to the motion of the ions along the ion string, and we are exciting the ions still along the ion string with the Rydberg excitation. Since the motion is quite so, the temperature of the ions is relatively high still for such a long ion crystal in our system. the motion is still significantly, and due to that, you get dephasing in the excitation process. And this causes part of this infidelity. We're currently changing the setup so that we can excite the ions from the side. And then this axial motion wouldn't cause this infidelity anymore. Advantage of that is also that we can focus our beams better to the individual ions, because we have a higher numerical aperture for focusing our laser beam. And with that, we also expect to get much higher Rabi frequency for the Rydberg excitation. So with that, we will also be able to make it faster and hopefully also increase the fidelity. Okay, it's not the only gate that is possible with Rydberg ions, and here just to give you a little bit of also an idea what also is possible in such a Rydberg ion string. I told you that the Rydberg state has a different trapping potential than the ground state due to this strong polarizability of the Rydberg levels. And there was a proposal by the Mainz group from Ferdinand Schmidt-Kahler and co-workers that propose to actually use this different trapping potential for strong state-dependent forces. So what you would do is you would give a classical electric field kick on the ions, and depending on whether it's in a ground state or a Rydberg state, it will the ion wave packet will have a different trapping potential. And depending on where it is, it will get now a different force and different kick here and different oscillation frequency. Okay, and you can use that so that the two wave packets after this electric field kick have a different trajectory, and depending on the trajectory, they get an effective geometric phase. And if you do the kick in the right way, back and forth, then you will return back to the motional ground state. And depending on the Rydberg state, where it is in the Rydberg state or ground state, it will get an effective phase with respect to each other. And you can use that for, again, a controlled phase gate. The group by Ferdinand has also calculated fidelities, how good fidelities they expect from such sequences, either using different pulse sequences here, also with some spin echo techniques. They can actually achieve fidelities that are significantly below 10 to the minus 2, also here limited by the lifetime. So on top of that, you see here also the timing. So it's also significantly below a microsecond, and you can really get small errors in such a gate, or expected errors in such a gate with really, really high speed. Okay, coming to the end of the talk, I think it's almost also time over, so it's probably good timing. So to summarize, I showed you a little bit of the physics of Rydberg ions. They combine the physics of trapped ions and Rydberg atoms. So of course, due to the fact that the ions are trapped in a pole trap, in a strong electric quadrupole field of a pole trap, you get very, very special effects. But it's actually interesting that we actually keep the ions trapped all the time. Okay, so it's in contrary to Rydberg atom experiments where most of the time people switch off their trap. We actually keep our trap on all the time, and you can even look at these motional effects even for implementing quantum gates and get strong forces and all of that. So I think it's a very, very interesting system. You can perform coherent Rydberg excitation. At the moment, we are still limited by laser powers and our focusing of our Rydberg lasers. We are currently working on that to improve that so that we can really get also high fidelity coherent Rydberg excitation. We see all the modified trapping potential. So we think that also motional interaction can be something like really interesting to look at in of the Rydberg ions. Quite state-dependent motional forces and so on can be interesting to look at in these Rydberg ions. And I showed you our results on a sub-microsecond 2-ion gate realized via the Rydberg interaction. So it's a new method for entangling Rydberg trapped ions, And we think it's actually quite interesting also because it doesn't slow down in long iron crystals. So, of course, in the future, we want to investigate its system for faster and high fidelity operations and also do some quantum computation in the end. Of course, I would like to thank the people who contributed to that. So the main PhD students that performed the gates and also the investigations on motional interaction were Shi, Fabian, and Jared. Both of them are now postdocs, unfortunately already in other groups. But there's also new PhD students, Shalina, Harry, and Marion, and they're doing a great job now. And of course, I want to also thank our theory collaborators, Igor and Weibin, and all the funding agencies that made it possible to make that. And of course, now I'm thank you for your attention, and I'm happy to answer more questions.
Thanks, Markus, for the excellent new things coming up in computing with trapped ions. Yeah. So there are a couple of questions here. The first one is about, can you elaborate on mirror grounding for the microwave, I guess?
Okay, so the grounding is actually, we experienced that the power of the microwave changes quite a bit due to the fact that the mirrors were not grounded. And the reason for that is just speculation to some extent. But of course, we actually sent this microwave into the ion trap with the electrodes very, very close to each other. And the wavelength of the microwave is actually a few millimeters, while the distance between the plates is only a bit between the blades from the ion trap is below a millimeter. So the microwave field will only enter in the near field next to these electrodes. And depending on the relative grounding of now the blades with respect to the mirrors that are somewhere outside, we expect that this actually changes the whole boundary conditions of the microwave there at the near field of our ion trap. Okay, but it's just a speculation. Of course, one would need to simulate that a bit more in detail to actually get to understand this effect a little bit more closely. But it made a huge difference to get the microwave power more stable at the position of the ions.
Okay, the next question is, what are the technical challenges which arise because of speed up of the gate?
The technical speed up of the gate?
Yeah.
Okay. I mean, of course, what we need to improve as technically is mostly the Rabi frequency of our Rydberg excitation laser. This is, on one hand side, as I said, we can focus our beams better to the ions from the side because of a high numerical aperture. We can expect a factor of 10 actually smaller focus with respect to coming from the axial direction. And with that, of course, we already achieve a Rabi frequency increase in fact of 5 or 10 or something like that, which will reduce the avidicity significantly. Of course, if you are faster in Rabi frequency, you might run into other problems. Of course, maybe at some point you need to, if you make the gate very fast, there will be effects of the trap in the end that you need to synchronize it maybe with your trap because the trap is driven at 18 megahertz. If you get closer to the 18 megahertz trap drive, you actually might want to look into synchronizing the whole gate with the trap. Of course, to get even higher Rabi frequencies and getting even faster, I think there we need to increase the laser power. I'd already told you the laser power drops by half from morning to evening. There's, of course, quite a lot of technical improvement to be made on that so that we can operate it for a longer time and maybe even at higher power. And yeah, the microwave power fluctuations are certainly a critical point in our gate scheme. Either we have some detector next to our trap to really stabilize it, probably even in near field of our ions, or having the microwave actually directly next to some horn or something like that next to the ion trap directly there, so that we don't get all the effects from sending it through free space from outside into the trap. I think that's something that we will need to work on. Apart from that, yep, I think we'll see what else we have as a technical problem in the end.
Okay, there is a last question, which is there anything that would prevent the integration of Rydberg ions into surface traps?
I think there's nothing really to prevent it, but I'm a bit afraid of surface effects for Rydberg ions. In particular, since, of course, the Rydberg ions or atoms are very, very sensitive to electric field fluctuations also. I mean, I showed you a lot of effects of the trapping potential, but if you now also go close to surfaces, all of these electric field fluctuations will also lead to decoherence. And I would still, even in probably next or after the next setup, first try to keep the ions a bit further away from surfaces than to immediately start with surface traps.
Okay, if I may ask one question, so can you go a few slides in the front? So meaning towards the end? Towards the end.
To the end.
Yeah.
Yes.
One more. More. I think the last one probably. The last one probably. Oh, yeah, here. So you show here two Rydberg excitation lasers, right? Just one slide back.
Okay. One more.
It's sorry. You have these two. I think the last part one. One more.
Maybe I go. You.
Summary slide.
Which number?
The next one. Next. Down.
That one?
No, down. Yeah, here. I think this slide. Yeah, that one. So you have two. What is shown here is two lasers, but you are not doing individual addressing, is it?
No. So this is what we are currently setting up.
You are setting up individual addressing.
Yes.
Then my question would be, if you go closer, would that be a problem for you?
So I mean, of course, it depends on which state you are. You can, of course, always hide ions in other Rydberg states, even if they're the next ones. Not in Rydberg states, in other D states, for instance, or S states, so that they are not excited to Rydberg's level. But the focusing for Rydberg lasers can be very, very good because it's a short wavelength, much better than for infrared lasers that we are usually using. And for the infrared lasers, you can achieve Rabi frequency errors, so that the neighboring ion sees a Rabi frequency of 2% of this ion. With the UV lasers, I think you can even suppress it better than that, so that you have probably 1% or less of Rabi frequency on a neighboring ion compared to that one. Yeah. But we have to see. I mean, of course, it's UV setup, and that's a bit more complicated also than for infrared.
Yeah, thanks. You also mentioned that you will go for higher Rydberg states, but then you also counter-argued that higher Rydberg state has more problem or may face problem of ionization because of the RF.
At some points you will get an ionization. Of course, there will be a quite clear limit when this will start to happen. I don't want to hide that already now we have some form of ionization happening. This is also limiting our statistics at the moment in measuring things. So what happens is that due to blackbody radiation, sometimes the Rydberg electron gets ionized. Unfortunately, at room temperature, for the Rydberg levels that we're using, it's one blackbody radiation photon is sufficient to ionize this electron. And this is not a big deal for Rydberg atom people because they always load new atoms. Okay, but for ions, it's a bit of an issue because it takes more time to reload ions. And sometimes we just have a doubly ionized ion in the trap. And if that happens, we have to throw it out and load new ions. And this usually takes, well, at the moment we use ablation loading, which already speeds up the system quite a bit. So maybe in a few seconds we can get ions again, but still it's taking time.
Okay, thanks. I don't see any other question at the moment. Okay.
Okay.
Thanks a lot for the excellent lectures.
Thanks a lot.
Yeah, and
thanks for the invitation, and really enjoyed the school.
Yeah, thank you very much for
the future lectures of the school also. Thanks a lot.
Thanks a lot.
Thank you for the lectures. Yes, thank you.
Have a nice afternoon, evening. Bye.
Bye. Take care.